There's a secret hidden in your pocket right now, something more powerful than cocaine, more addictive than slot machines, more precisely engineered to hijack your brain than any drug a chemist could synthesize. And you probably checked it within the last 10 minutes. But here's what makes this truly disturbing. The same mechanism that makes you reach for your phone at 3 in the morning, that makes scrolling feel impossible to stop, that creates that small panic when you can't find it. That exact same neurological pathway is what traps a heroin user in their addiction, what drives a gambler to bet their last dollar, what makes an alcoholic reach for one more drink despite losing everything. Tonight, we're going to discover something that will change how you see every choice you make. Because what if I told you that addiction isn't really about the drug? What if it's not about willpower or moral failure? What if instead, addiction is your brain doing exactly what evolution designed it to do, but in a world it was never designed to encounter? Here's the twist that researchers discovered, the one that changed everything. Every person who's ever said, "I can stop whenever I want," was telling the truth. They can stop. They do want to stop. The terrifying part is that wanting to stop and being able to stop involve two completely different brain systems, and addiction is what happens when one hijacks the other. By the end of tonight, you'll understand why the most successful, disciplined person can lose everything to a substance they know is destroying them. Why your teenager, brilliant and capable in every other way, can't put down their phone. Why someone can simultaneously desperately want recovery and be utterly unable to achieve it. And you'll discover something even more unsettling. In the last 20 years, we've accidentally created the most addictive environment in human history. The evidence is in your hand right now. The scale of what we're dealing with is staggering, but the numbers themselves hide the real story. Globally, around 240 million people struggle with substance use disorders. But that's just what we can measure, just what fits into diagnostic categories. Add in behavioral addictions, gambling, gaming, compulsive internet use, and the number grows exponentially. But here's the reveal that stopped researchers in their tracks. When neuroscientists put people in brain scanners, some addicted to heroin, some to gambling, some who couldn't stop checking social media, they saw something impossible to ignore. The brain patterns were nearly identical. The same regions lighting up, the same circuits being activated, the same neurochemical dance unfolding. A gambling addiction, they discovered, doesn't just resemble a drug addiction. At the level of neurons and neurotransmitters, it essentially is the same thing. Your brain cannot tell the difference between the high from cocaine and the high from winning at cards. Both are, fundamentally, hijacking an ancient system that was never designed to encounter either. And here's what makes this finding so crucial. The same person who exhibits ironclad self-control in one area of life, maintaining a rigorous exercise routine, excelling in a demanding career, managing complex relationships, can find themselves utterly powerless when their reward system is hijacked. This isn't hypocrisy. This isn't weakness. This is neurobiology. For most of human history, we got this completely wrong. The person who couldn't stop drinking, who gambled away their family's security, who allowed a substance to destroy their life, we labeled them weak, immoral, lacking in character. That perspective still lingers today, adding a layer of shame to a condition that is, in truth, a complex cascade of brain chemistry, genetic vulnerability, environmental factors, and learned behavior that can happen to anyone. The breakthrough came in the 1970s and 80s, when researchers began mapping the brain's reward circuits in unprecedented detail. What they discovered fundamentally changed everything. Every substance and behavior with addictive potential activates the same pathway in the brain. Whether cocaine, alcohol, heroin, gambling, or gaming. The mesolimbic dopamine system lit up in distinctly similar patterns. This was the first clue that we'd been looking at addiction all wrong. It wasn't about the drug, it was about the pathway. But this discovery immediately raised a more unsettling question, one that haunted researchers for decades. If everyone has the same reward circuitry, why do only some people become addicted? Why can one person enjoy wine with dinner for 40 years without issue, while another has one drink and finds themselves on an inexorable slide toward alcoholism? Why does one teenager try a drug at a party and walk away, while another begins a descent they can't reverse? The answer, when it finally emerged, was both elegant and disturbing. Genetics account for approximately 40 to 60% of addiction vulnerability, based on extensive twin studies comparing identical twins who share 100% of their DNA with fraternal twins who share roughly 50%. This is a substantial contribution, roughly equivalent to the genetic component of height or diabetes. But here's the crucial twist. Genes don't cause addiction. They create vulnerability. Your genes might load the gun, as researchers sometimes phrase it, but your environment pulls the trigger. And even that metaphor is too simple. Because the relationship between genes and environment isn't linear, it's recursive, circular, each influencing the other in feedback loops that span from before birth through every stage of life. Some people carry genetic variants that make them highly sensitive to rewards, meaning natural pleasures feel less satisfying, potentially driving them to seek more intense stimulation. Others carry variants affecting impulse control, stress response, or emotional regulation, all increasing the odds that experimentation becomes compulsion. But here's what the research revealed that changed the conversation. Those same genetic variants that increase addiction risk in harsh, traumatic environments can actually confer advantages in supportive, nurturing ones. This pattern, called differential susceptibility, suggests that some people aren't simply more vulnerable, they're more sensitive to their environment, period. For better or worse. This means that the same genetic profile that leads one person toward addiction in an unstable, stressful environment might lead another person toward extraordinary success in a stable, nurturing one. The vulnerability is also a kind of responsiveness. The risk is also a potential. Now consider what might be the perfect storm for addiction vulnerability: the adolescent brain. Neuroscientific research has uncovered something that explains so much about why teenage years are so treacherous. The prefrontal cortex, your brain's executive, the region responsible for impulse control, planning, weighing consequences, rational decision-making, doesn't fully mature until sometime in the mid-20s. Brain imaging studies using MRI technology have documented this progressive maturation, watching as the prefrontal cortex gradually develops the neural architecture needed for adult-level self-control. Meanwhile, the reward centers, the nucleus accumbens, the ventral tegmental area, are not just active during adolescence, they're hyperactive. They're lighting up more intensely, responding more vigorously to potential rewards than they will at any other point in the lifespan. This creates a neurological perfect storm, a brain exquisitely sensitive to rewards, but poor at evaluating long-term consequences. The gas pedal is pressed to the floor while the brakes are still being installed. Teenagers aren't trying to be reckless. Their brains are literally wired for this exact pattern, to seek novel, rewarding experiences while the neural systems that might say, "Wait, maybe this is a bad idea," are still under construction. From an evolutionary perspective, this design makes sense. Adolescence is when humans historically needed to explore, take risks, separate from family, and establish themselves. But in a modern world where those risks include addictive substances and behaviors, this developmental window becomes a period of profound vulnerability. And the statistics bear this out in a striking way. Approximately 90% of people with substance use disorders began using before age 18, based on retrospective studies examining age of first use among adults in treatment. Early exposure during this critical developmental window, combined with a brain still forming, creates conditions where addiction can take root with frightening efficiency. But here's the hopeful twist in this: revelation. Understanding these vulnerabilities opens pathways for prevention and early intervention that previous generations never imagined possible. If we know the brain is most vulnerable during adolescence, if we understand the specific neurological factors creating that vulnerability, we can design interventions targeting exactly that window, exactly those mechanisms. Then there's trauma, and this is where the story becomes deeply personal for millions of people. The Adverse Childhood Experiences study, published by researchers Felitti and Ander in the late 1990s, stands as one of the most important pieces of addiction research ever conducted. They surveyed over 17,000 adults about childhood experiences and tracked health outcomes over time. What they found was a dose-response relationship so clear it was undeniable. Each additional adverse experience, abuse, neglect, household dysfunction, witnessing violence, incrementally increased the likelihood of developing addiction later in life. Someone with 4 or more adverse childhood experiences was 7 times more likely to develop alcoholism than someone with none. The numbers were similarly stark for drug use disorders. This wasn't correlation hiding in statistical noise. This was a clear, measurable pattern. But here's what makes this finding so crucial. The research strongly suggests that trauma doesn't just create psychological scars. It appears to fundamentally alter how the brain's stress response systems develop and function. The hypothalamic pituitary adrenal axis, which regulates our response to stress, seems to become dysregulated in people who experience significant early trauma. Brain imaging studies have found differences in both structure and function in regions involved in threat detection and emotional regulation. What this could imply is that people with trauma histories aren't experiencing normal stress responses. They're living in a state of chronic hyperarousal, where their brain constantly signals danger even in safe situations. Based on what we observe clinically, substances appear to offer a way to chemically regulate what the brain can no longer manage on its own. It's not weakness, it's a form of self-medication, an attempt to solve a very real neurological problem, even though it ultimately creates new ones. The pattern treatment providers see repeatedly is this. Someone experiences trauma. Their stress systems become dysregulated. They discover that alcohol or drugs or even compulsive behaviors temporarily quiets the alarm that's constantly ringing in their brain. What began as relief becomes dependency. What began as solution becomes problem. This suggests why treating only the substance use while ignoring the underlying trauma so often fails. You're essentially telling someone to give up their primary coping mechanism for managing a severe, ongoing stress response, without first providing alternative tools or addressing the root dysregulation. And then we arrive at the present moment, at the unprecedented experiment we're all living through right now. The smartphone in your pocket contains more addictive potential than a casino, a pharmacy, and a liquor store combined. That's not hyperbole. Let me show you why. Unlike substances that need to enter your bloodstream to affect your brain, your phone delivers something equally powerful through a different route: variable rewards on demand. Every notification represents a potential dopamine hit. Every swipe could reveal something pleasurable. The unpredictability, Will this next scroll show you something funny, surprising, enraging, or disappointing? Creates the same reward prediction error that slot machines were engineered to exploit, that cocaine triggers, that keeps a gambling addict pulling the lever. But here's the reveal that should genuinely disturb you. The design patterns we see aren't accidental. Documented reports reveal that tech companies have employed specialists in behavioral psychology and user engagement to design their products. Whether the explicit goal is addiction or simply maximizing engagement, the techniques being used, variable reward schedules, notification timing, infinite scroll, and gamification elements, are drawn from the same psychological principles that underlie addictive behavior. These companies have access to the same neuroscience research we're discussing tonight, and the resulting products function, in practice, in ways that make them extraordinarily difficult to put down, regardless of the designer's stated intentions. Research tracking actual smartphone usage patterns has found that the average person checks their device approximately 58 times per day, with nearly half of those checks occurring within 3 minutes of the previous check. These aren't conscious, deliberate decisions to engage with technology. The pattern resembles compulsive behavior, driven by neural circuits that have learned to expect rewards from the device. We are living through an unprecedented experiment in human history. Never before has such immediate, potent, and varied stimulation been available 24 hours a day, carried in pockets and purses, generating notifications specifically designed to interrupt whatever we're doing and pull us back in. The long-term consequences are still unfolding, but early research paints a concerning picture. Our collective vulnerability to addiction, not just to substances, but to behaviors that hijack reward systems, may be higher than at any point in human history. And the people most vulnerable? Adolescents, whose hyperactive reward systems and underdeveloped impulse control make them exquisitely sensitive to exactly these mechanisms. Yet within this sobering landscape, there is profound hope. The same neuroscience that has revealed how addiction develops has also illuminated pathways to recovery. The brain, it turns out, is remarkably plastic, capable of healing, rewiring, and forming new patterns even after years of addiction. The prefrontal cortex can regain control over impulsive drives. The sensitivity of reward receptors can normalize. The learned associations between cues and cravings can be gradually weakened and replaced with new, healthier connections. This journey we're embarking on tonight will take us deep into the mechanisms of addiction, from the molecular dance of neurotransmitters to the sweeping influence of culture and policy. We'll explore how a system designed to help us survive has become, in our modern world, a source of profound vulnerability. We'll examine substance addictions that have plagued humanity for centuries, behavioral addictions that have existed as long as gambling and games, and digital addictions that represent entirely new challenges for our ancient brains. But more than anything, we'll see addiction not as a moral failure or a hopeless condition, but as a medical disorder rooted in neurobiology, shaped by psychology and influenced by social factors, a disorder that, with proper understanding and treatment, carries tremendous potential for recovery. So take a slow breath. Let your mind settle into the quiet curiosity of exploration. Because what we're about to discover isn't just about addiction, it's about the fundamental nature of human desire, motivation, and the remarkable ways our brains navigate a world they were never designed to encounter. The brain's reward system, architecture of desire. Deep in the center of your brain, nestled beneath the cortex where conscious thought unfolds, lies a network of structures so ancient, so fundamental to survival, that it predates human consciousness itself. This is the reward system, a circuit of neurons and neurotransmitters that exists for one primary purpose: to ensure that behaviors essential for survival feel good enough to repeat. When our distant ancestors found food after days of hunger, this system flooded their brains with signals of satisfaction and relief. When they successfully reproduced, ensuring the continuation of their genetic line, these same circuits activated with intensity. When they formed social bonds that increased their chances of survival, the reward system reinforced those connections with feelings of warmth and belonging. This wasn't luxury or excess. This was evolution's solution to a fundamental problem: how to make creatures pursue what they need to survive without requiring conscious deliberation every single time. The architecture of this system, mapped in exquisite detail over the past half-century, centers on several key structures working in concert. At the heart lies the ventral tegmental area, or VTA, a small cluster of neurons in the midbrain that serves as the primary source of dopamine for the reward circuit. When something rewarding occurs, or when we anticipate something rewarding, these neurons fire in bursts, releasing dopamine that travels along specific pathways to other brain regions. The most famous destination for this dopamine is the nucleus accumbens, sometimes called the brain's pleasure center, though that label is somewhat misleading. The nucleus accumbens doesn't simply process pleasure. It's more accurately described as a processor of motivational salience. It helps determine what's worth paying attention to and what's worth pursuing. When dopamine from the VTA reaches the nucleus accumbens, it creates a signal that essentially says, "This is important. Remember this. Do this again." But the reward circuit doesn't stop there. Dopamine projections also reach the prefrontal cortex, the brain's executive center, where they influence decision-making, planning, and impulse control. They connect to the amygdala, where emotional memories are formed and stored. They interact with the hippocampus, crucial for learning and memory. The result is an integrated network that links reward detection with memory, emotion, and decision-making, a system designed to learn from experience and guide future behavior. Understanding dopamine's role in this system is crucial. And here's where we encounter one of the most important discoveries in addiction neuroscience, one that completely changed how we understand compulsive behavior. For decades, dopamine was called the pleasure chemical. You do something enjoyable, your brain releases dopamine, you feel good. Simple, right? Completely wrong. The breakthrough came in the 1990s from Wolfram Schultz's laboratory at the University of Cambridge. His team trained monkeys to associate a cue, a light or sound, with a reward: a sip of juice. Initially, the monkeys' dopamine neurons fired when they received the juice, exactly as expected. But after repeated training, something extraordinary happened. The dopamine neurons began firing not when the juice arrived, but when the cue appeared, when the monkeys anticipated the reward. The pleasure itself wasn't generating the dopamine spike. The prediction was even more revealing. If the expected reward failed to arrive, dopamine activity didn't just return to baseline, it plummeted below baseline, creating a signal that essentially screamed, "Something is wrong, an expectation was violated, fix this immediately." This discovery fundamentally rewrote our understanding of addiction. Dopamine isn't primarily about experiencing pleasure. It's about learning to predict rewards and then being driven to pursue them. It's the chemical messenger of wanting, far more than liking, to use the critical distinction coined by addiction researchers Kent Berridge and Terry Robinson. And here's why this matters so profoundly. It explains why people continue to compulsively pursue substances or behaviors long after they stop finding them pleasurable. The wanting persists even when the liking has completely faded. You'll meet people deep in addiction who will tell you honestly, "I don't even enjoy using anymore," and they're telling the absolute truth. But their brain's wanting system, sensitized to drug cues, continues to generate overwhelming motivation to use. This is the neurological basis of one of addiction's cruelest patterns. You can simultaneously hate what you're doing and be unable to stop doing it. Because you're not being driven by pleasure, you're being driven by a prediction error system that's been hijacked. In a healthy reward system, this prediction and pursuit mechanism works beautifully. You learn that studying leads to good grades, which leads to future opportunities. You learn that exercising makes you feel energized and healthy. You learn that meaningful conversations with friends provide connection and support. The dopamine system helps stamp in these associations, making it more likely you'll repeat these beneficial behaviors in the future. Natural rewards, the things your brain evolved to find pleasurable, have built-in limits. Eating food, even delicious food, stops feeling rewarding once you're full. Your body's homeostatic mechanisms ensure you don't keep eating indefinitely. Sexual activity, social interaction, winning at games all produce temporary dopamine increases that eventually return to baseline. The reward system activates, the behavior gets reinforced, then it subsides, allowing the brain to return to equilibrium. This is healthy. This is how the system is supposed to work. Addictive substances and behaviors, by contrast, exploit this system in ways that evolution never prepared it for. And here's the number that changes everything. Research using positron emission tomography, PET scans, has documented that drugs like cocaine can increase dopamine levels in the nucleus accumbens by 3 to 10 times the amount produced by natural rewards. Methamphetamine produces even larger surges. Even alcohol, working through indirect mechanisms, can significantly elevate dopamine in key reward regions beyond natural levels. 3 to 10 times. That's not a subtle difference. That's not a bit more pleasant than eating chocolate. This is a qualitative difference that fundamentally breaks how the reward system operates. When dopamine floods the synapse at these super-physiological levels your brain was never designed to encounter, it creates an experience so intense that your brain essentially tags it as more important than survival itself. The memory of this experience becomes indelibly encoded, linked to every cue present at the time. The people you were with, the place where it happened, the specific sights, sounds, even smells of the environment. These associations form with a strength and speed that natural learning processes rarely achieve. Your brain is essentially saying, whatever just happened is more important than food, more important than sex, more important than anything. Remember every detail. This is why people throw away careers for drugs, why they abandon families, why they risk their lives. It's not that they value these things less than you do. It's that their brain has been convinced, at a level below conscious thought, that the drug is more essential to survival than these other things actually are. But here's where the brain's remarkable adaptive capacity becomes its own worst enemy, and where the true trap of addiction springs shut. The reward system is designed to adjust to consistently high levels of stimulation. It has to be, or you'd become addicted to eating the first time you enjoyed a meal. When a stimulus keeps producing large dopamine surges, the brain compensates through a process called downregulation. It reduces the number of dopamine receptors in the postsynaptic neuron and decreases dopamine production in the VTA neurons. This is the neurological basis of tolerance. The same dose that once produced intense effects gradually produces smaller and smaller responses as your brain adapts. But tolerance creates a devastating secondary problem that many people don't realize until they try to quit. As the brain reduces its dopamine signaling capacity in response to artificial drug-induced elevation, natural rewards, food, social interaction, achievements, sex, music, everything that normally makes life feel worthwhile, begin to feel flat, empty, pointless. They're producing the same amount of dopamine they always did. but there are now fewer receptors to receive the signal. The volume has been turned down on everything except the drug. This state is called anhedonia, the inability to experience pleasure. And this is one of addiction's most tragic patterns, the progressive narrowing of what feels worthwhile. Hobbies that once brought joy gradually lose their appeal. Relationships that once felt meaningful start to feel like obligations. Goals that once motivated you seem hollow. This isn't depression, though it looks similar. This isn't losing interest in some philosophical sense. This is neurochemical. Your reward system has been recalibrated around an artificially intense stimulus, and everything else pales by comparison. And here's the cruel part. When nothing feels good except the drug becomes the only thing that makes life bearable. What began as seeking pleasure becomes desperately seeking relief from the flatness, the emptiness, the anhedonia that now pervades everything. The situation becomes even more complex when we consider how the reward system interacts with learning and memory systems. The hippocampus and amygdala don't just passively store information about drug experiences, they actively strengthen synaptic connections in response to the intense dopamine signaling. This process, called long-term potentiation, is the same mechanism that underlies all learning, but it operates with particular intensity in the context of addiction. The result is that drug-related memories become extraordinarily persistent and resistant to extinction. A person might consciously decide they want to quit, might understand all the negative consequences of continued use, might have every rational reason to stop, but years later, encountering a cue associated with previous drug use can trigger powerful cravings. The sight of drug paraphernalia, a specific location, even certain times of day or emotional states can all reactivate these deeply encoded memories, producing dopamine release that can feel as urgent as hunger or thirst. This is why relapse prevention is such a crucial focus in addiction treatment. It's not enough to simply detoxify the body and wait for the acute withdrawal symptoms to pass. The learned associations, the neural pathways that link cues to cravings, can persist for months or even years. Effective treatment requires systematically identifying these triggers, developing coping strategies, and gradually weakening the cue-response associations through repeated exposure without reinforcement. Recent research has also revealed the important role of another neurotransmitter system in the reward circuit, the endogenous opioid system. This system, which includes naturally occurring chemicals like endorphins and enkephalins, interacts intimately with the dopamine system to influence reward processing. The endogenous opioids don't just modulate pleasure, they also affect how we evaluate and remember rewarding experiences. Different drugs engage these systems in different ways. Opioids like heroin or prescription painkillers directly activate mu-opioid receptors, producing intense euphoria while simultaneously triggering dopamine release. Stimulants like cocaine and methamphetamine primarily work by blocking the reuptake of dopamine, causing it to accumulate in the synapse. Alcohol affects multiple neurotransmitter systems, including GABA and glutamate, but ultimately triggers dopamine release in reward pathways. Cannabis works through the endocannabinoid system, another modulatory system that influences dopamine neurons. Despite these different mechanisms of action, all roads lead back to dopamine elevation in key reward regions, which is why neuroscientists sometimes refer to dopamine as the final common pathway of addiction. No matter what substance someone uses or what behavior they're engaging in, if it has addictive potential, it's affecting this dopamine circuit. This universal mechanism also helps explain why behavioral addictions, gambling, gaming, social media use, can produce symptoms remarkably similar to substance addictions. They don't introduce external chemicals into the brain, but they don't need to. By providing unpredictable rewards at variable intervals, they trigger the reward system's dopamine response. The brain doesn't distinguish between pleasure from a chemical and pleasure from a behavior. It simply responds to the signal that something rewarding has happened or is about to happen. The concept of reward prediction, error, introduced earlier, becomes particularly relevant here. When we encounter something more rewarding than expected, dopamine neurons fire vigorously, encoding the positive surprise. When something is exactly as rewarding as predicted, they fire at a steady baseline. When something is less rewarding than expected, their firing drops below baseline, encoding disappointment or prediction error. Gambling exploits this mechanism perfectly. The unpredictability of whether the next spin, the next hand, the next roll will win creates a constant state of anticipation. Each time, the brain is making a prediction, and each time, the outcome is uncertain. This sustained engagement of the reward prediction system creates a psychological state remarkably similar to drug intoxication. Focused, energized, oblivious to other concerns. Social media platforms have inadvertently, or perhaps deliberately, given the involvement of behavioral psychologists in their design, recreated these same conditions. When you pull down to refresh your feed, you never know what you'll see. Will it be something funny? Something enraging? Something boring? This uncertainty keeps you checking, because each check represents a potential reward prediction, and the brain loves to make predictions about rewards. Understanding the reward system's architecture isn't just an academic exercise. It's the foundation for comprehending why addiction is so difficult to overcome through willpower alone. We're not dealing with a simple choice to pursue pleasure over responsibility. We're dealing with a system that has been fundamentally reprogrammed, where the normal signals that guide behavior have been overwhelmed by artificially intense stimuli, where learning and memory systems have encoded drug-related associations with a strength that rivals or exceeds the encoding of survival-critical information. This knowledge also points toward more effective treatment approaches. If addiction is primarily a problem of hijacked reward circuits and maladaptive learning, then treatment should focus on helping the brain form new associations, on gradually resensitizing reward systems to natural reinforcers, on strengthening the prefrontal cortex's ability to override cue-triggered cravings. This is precisely what many evidence-based treatments do, though they might describe their mechanisms in different terms. The reward system, designed over millions of years to help animals and humans survive and thrive, has become, in our modern world, a source of profound vulnerability. But it's also, remarkably, a source of hope, because the same plasticity that allows these systems to be hijacked also allows them to heal, to rewire, to learn new patterns. The brain that learned to associate certain cues with drug use can learn to associate them with recovery instead. The dopamine system that became hypersensitive to drugs can gradually return to normal sensitivity. The prefrontal cortex that lost its ability to inhibit impulses can regain that control. Understanding how the reward system works, how it can be corrupted, and how it can potentially be restored. This is the foundation upon which our entire understanding of addiction rests. Neurological transformations, the three-stage cycle. If the reward system is the stage on which addiction plays out, then the three-stage cycle of addiction is the script that unfolds upon it. This model, articulated most clearly by addiction researchers George Koob and Nora Volkov, describes addiction not as a static state, but as a recursive process. A cycle that perpetuates itself through distinct neurobiological changes in specific brain circuits. The first stage is binge and intoxication. This is the stage most people associate with addiction, the actual consumption of drugs or engagement in the addictive behavior. But calling it simply getting high misses the profound neurobiological events occurring. During this stage, the reward circuits we discussed, the ventral tegmental area, nucleus accumbens, and associated structures in the basal ganglia, become hyperactivated. Dopamine floods the system. Endogenous opioids are released. The subjective experience is one of intense euphoria, reduced anxiety, or temporary escape from psychological pain. What makes this stage addictive isn't just that it feels good. Many things feel good. What makes it addictive is how it feels good. The intensity, the speed of onset, and the powerful activation of learning systems that encode every detail of the experience. The brain's reward circuits are essentially shouting, "Pay attention, this is important. Remember everything about this moment, so we can repeat it." During early experimentation with drugs or early gambling experiences, the prefrontal cortex is still somewhat engaged. A person might think, "This is fun, but I need to be careful." They might experience moments of concern or self-awareness. But as use continues and the cycle progresses, something fundamental begins to change in the balance of power between different brain systems. The basal ganglia, a collection of structures deep in the brain, includes not just the nucleus accumbens, but also the dorsal striatum, a region involved in habit formation. With repeated drug use, activation gradually shifts from the ventral, reward-focused regions of the striatum to the dorsal, habit-focused regions. This transition marks a critical point in the development of addiction, the shift from action-outcome learning to stimulus-response habits. In practical terms, this means that what began as a deliberate choice to use a drug for its pleasurable effects gradually becomes an automatic behavior triggered by specific cues. The person no longer uses primarily for pleasure, they use because the cue, stress, a specific time of day, a particular location, automatically triggers the behavior. The dorsal striatum has essentially created a habit loop that bypasses higher-order decision-making processes. This is why people in advanced stages of addiction often report that they don't even enjoy using anymore. They're not chasing the high they once experienced. They're following a script their brain has written, a habit so deeply encoded that it feels as involuntary as hunger or thirst. But binge and intoxication, intense as it is, represents only 1/3 of the cycle. The second stage is withdrawal and negative effect, and in many ways, this stage is more powerful in driving continued addiction than the pleasure of intoxication itself. The brain is a homeostatic organ. It constantly seeks equilibrium. When a drug repeatedly floods the system with dopamine or other neurotransmitters, the brain adapts by reducing its own production of these chemicals and decreasing receptor sensitivity. This is the tolerance we discussed earlier. But these adaptations, which occur relatively quickly, don't reverse immediately when drug use stops. The result is a state of neurochemical depletion. Dopamine levels fall below normal, endogenous opioid signaling is reduced, and a host of other neurotransmitter systems are thrown out of balance. The subjective experience of this state depends somewhat on which substance or behavior was being used, but common elements include profound dysphoria, a state of feeling terrible that goes beyond simple sadness. There's often intense anxiety, irritability, and a pervasive sense that nothing will ever feel good again. Physical symptoms can include sleep disturbances, changes in appetite, and heightened sensitivity to pain. This isn't just unpleasant, it's agonizing, particularly for someone whose brain has lost the ability to produce normal levels of positive feeling on its own. Here's where the neurobiology becomes especially insidious. The brain region most active during withdrawal isn't the reward system, it's the extended amygdala, a collection of structures including the central nucleus of the amygdala and the bed nucleus of the stria terminalis. These regions, central to processing threat and stress, become hyperactive during withdrawal. They're essentially sounding an alarm. Something is wrong, danger is present, urgent action is needed. This activation involves a different set of neurotransmitters than the reward stage. Stress hormones like corticotropin-releasing factor flood the system. Dynorphin, an endogenous opioid that produces dysphoric rather than euphoric effects, is released. Norepinephrine signaling increases, contributing to the physical symptoms of withdrawal. The entire system is pushing the organism toward a single conclusion. I need to make this stop. And there's an obvious way to make it stop. Use the drug again. The substance that created this neurochemical crisis is also, temporarily, the cure for it. This is the dark logic of the withdrawal stage. What began as seeking pleasure becomes, increasingly, seeking relief from pain. The motivation shifts from positive reinforcement, using to feel good, to negative reinforcement, using to avoid feeling terrible. Research has shown that this shift has profound implications for addiction trajectories. People in the early stages of addiction might use primarily for the euphoric effects, and periods of abstinence, while perhaps unpleasant, don't produce severe withdrawal symptoms. But as addiction progresses and the brain adapts to chronic drug exposure, the withdrawal stage becomes increasingly severe and increasingly motivating. People use not to get high, but to feel normal, to quiet the screaming of an extended amygdala that has been sensitized to interpret the absence of drugs as a crisis. This stage also involves another critical change: the kindling effect. Originally observed in the context of alcohol withdrawal, kindling refers to the phenomenon where repeated cycles of intoxication and withdrawal make each subsequent withdrawal more severe. The neural circuits involved in withdrawal become sensitized, so that even after long periods of abstinence, a return to use followed by withdrawal can produce symptoms more severe than those experienced during previous withdrawal episodes. The kindling effect helps explain why relapse can be so dangerous. Someone might successfully detox, maintain abstinence for weeks or months, then relapse for a short period. When they try to stop again, the withdrawal symptoms can be more intense than they remember, creating an even stronger motivation to continue using. The third stage of the cycle is preoccupation and anticipation, and this stage represents perhaps the most challenging aspect of addiction to treat, because it can persist long after physical withdrawal has resolved. This stage is characterized by a state of constant mental preoccupation with obtaining and using the drug, accompanied by a reduced ability to resist urges to use, even when the person genuinely desires to quit. The primary brain regions involved in this stage are structures in the prefrontal cortex, particularly the orbitofrontal cortex and dorsolateral prefrontal cortex, and their connections to the limbic system. These are the brain's executive control regions, responsible for planning, decision-making, impulse inhibition, and maintaining behavior in pursuit of long-term goals. Neuroimaging studies of people with substance use disorders have consistently shown altered function in these prefrontal regions. They show reduced gray matter volume, decreased metabolic activity, and altered connectivity with other brain regions. Functionally, this translates to impaired ability to inhibit prepotent responses, to stop themselves from acting on impulses even when they consciously want to stop. This isn't a matter of willpower in the traditional sense. Someone might sincerely want to quit, might understand all the reasons they should quit, might have made firm commitments to quit. But when confronted with drug cues, or when experiencing craving, the impaired prefrontal cortex simply can't generate enough inhibitory signal to override the powerful motivation rising from reward and stress circuits. The preoccupation stage also involves a phenomenon called incubation of craving. discovered through animal research but confirmed in human studies. Remarkably, drug cravings triggered by environmental cues can actually increase during early abstinence rather than decrease. Rats taught to self-administer cocaine and then forced to abstain show increasing responses to drug-related cues over the first several weeks of abstinence before those responses begin to decline. In humans, this manifests as a particularly dangerous period in early recovery. Someone might successfully complete detox, might be feeling physically better, might be thinking clearly again, and then find that their cravings are actually worse than they were during active use. This isn't a failure of treatment or a sign that recovery is impossible. It's a predictable neurobiological phenomenon reflecting changes in how the brain processes drug-related memories and cues during abstinence. The preoccupation stage also involves disruption of executive function more broadly. Studies using neuropsychological tests show that people with substance use disorders often have difficulty with working memory, holding information in mind and manipulating it, cognitive flexibility, adapting to changing circumstances, and planning for the future. These aren't permanent deficits. They typically improve with sustained abstinence, but during active addiction, they create a vicious cycle where the very cognitive skills needed to successfully quit are impaired. Understanding these three stages as a cycle is crucial. They don't occur in strict sequence and then stop. Instead, they form a self-perpetuating loop. Intoxication leads to neuroadaptations that make withdrawal more severe, which increases the motivation to use again to find relief, which further strengthens the habit pathways and weakens executive control, which makes it harder to resist cues and cravings during the preoccupation stage, which leads back to intoxication. Each revolution through the cycle deepens the neurological changes, making the pattern more entrenched. But the cycle model also offers hope, because understanding these distinct stages allows for targeted interventions. Medications can help ease withdrawal symptoms, reducing the negative reinforcement that drives continued use. Cognitive behavioral therapies can help identify and manage the cues that trigger preoccupation and craving. Training in executive function and mindfulness can help strengthen prefrontal control over impulsive behavior. By addressing each stage with appropriate interventions, the cycle can be interrupted, giving the brain time to begin healing. One of the most important discoveries in addiction neuroscience has been recognizing that these changes, while profound, are not permanent. The term brain disease has sometimes been interpreted to mean irreversible damage, but research on neuroplasticity has shown this isn't the case. With sustained abstinence, dopamine receptors can upregulate again. Prefrontal cortex function can improve. The balance of power between reward circuits and executive control regions can shift back toward healthier patterns. This doesn't happen quickly. Brain healing takes time, often many months, and it doesn't happen automatically. It requires active engagement in recovery, often with professional support. But it does happen. Studies following people in recovery over years have documented progressive improvements in brain structure and function, corresponding with improvements in decision-making, impulse control, and overall quality of life. The three-stage cycle of addiction represents one of neuroscience's most complete models of how a complex behavioral disorder emerges from changes in specific brain circuits. It explains why addiction is so much more than a simple pleasure-seeking behavior, why it's so difficult to quit through willpower alone, and why effective treatment requires addressing multiple neurobiological systems simultaneously. It also serves as a powerful reminder that addiction is not a character flaw or a moral failing. It's a medical condition arising from how our brains respond to certain stimuli in certain contexts. Understanding this doesn't absolve people of responsibility for their actions, but it does contextualize those actions within a neurobiological framework that makes compassion not just kind, but scientifically accurate. Genetic architecture of vulnerability, the heritable component. If you were to gather 100 people in a room and expose them all to the same potentially addictive substance under identical circumstances, something fascinating would happen. Their responses would vary dramatically. Some would experience intense pleasure and rapidly develop problematic use patterns. Others would use occasionally without progression. Some might try it once and find it unpleasant enough never to try again. This variance, the observable differences between individuals in identical circumstances, is one of science's clearest signals that genetic factors are at play. Twin studies, the gold standard for disentangling genetic from environmental influences, have consistently demonstrated that addiction has a substantial heritable component. The methodology is elegant. Compare identical twins who share 100% of their DNA with fraternal twins who share approximately 50%. If a trait is influenced by genetics, identical twins should be more similar than fraternal twins. For addiction, this pattern is striking. Heritability estimates for substance use disorders range from approximately 40 to 70%, depending on the specific substance and the population studied. Alcohol dependence shows heritability, estimates between 48 and 66%. Cannabis addiction heritability is estimated at 51 to 59%. Cocaine dependence ranges from 42 to 79%, with some variation by sex. Nicotine dependence falls between 33 and 71%. These are substantial figures, comparable to the heritability of height or certain chronic medical conditions like diabetes. But what does heritability actually mean? This is often misunderstood. A heritability of 60% doesn't mean that 60% of addiction is genetic and 40% environmental. Rather, it means that 60% of the variance in addiction risk across a population can be attributed to genetic differences between individuals. The distinction is subtle but critical. Genes don't cause addiction. They modulate risk in complex interaction with environmental factors. The search for specific genes contributing to addiction vulnerability has been challenging, precisely because addiction is what geneticists call a complex polygenic trait. Unlike single-gene disorders like Huntington's disease or cystic fibrosis, addiction involves many genes, each contributing a small effect, interacting with each other, and with environmental factors in ways that are difficult to predict. Still, researchers have identified several categories of genes that contribute to addiction risk. Some are substance-specific, affecting how a person metabolizes or responds to particular drugs. The classic example is the ALDH2 gene, which encodes aldehyde dehydrogenase, an enzyme involved in alcohol metabolism. A variant of this gene, common in East Asian populations, produces an enzyme that works less efficiently, causing acetaldehyde, a toxic metabolite of alcohol, to accumulate. The result is facial flushing, nausea, and general discomfort when drinking alcohol, what's sometimes called the alcohol flush reaction. This genetic variant powerfully reduces alcohol dependence risk. People carrying this variant are significantly less likely to develop alcohol use disorders, not because they're morally superior or have stronger willpower, but because their genetic makeup makes drinking alcohol physically unpleasant. This is one of the clearest examples of how genes can directly influence addiction vulnerability through their effects on drug metabolism. Another substance-specific gene is OPRM1, which encodes the mu opioid receptor, the primary target for drugs like heroin, morphine, and prescription painkillers. Variants of this gene affect how effectively these drugs activate their receptors, influencing both the intensity of the euphoric effects and the development of physical dependence. People with certain OPRM1 variants may experience stronger effects from opioids, potentially increasing their risk for developing problematic use. For nicotine, genes encoding nicotinic acetylcholine receptors, particularly the CHRNA5, CHRNA3, CNB4 gene cluster, have been consistently associated with smoking behavior and nicotine dependence. These genes affect how nicotine binds to receptors in the brain, influencing both the reinforcing effects of smoking and the severity of withdrawal symptoms. But beyond these substance-specific genes, there's a second, perhaps more important category: genes that affect general addiction, vulnerability across multiple substances. These genes typically influence core features of reward processing, impulse control, stress response, or emotional regulation, psychological dimensions that affect risk for all addictive disorders. The DRD2 gene, encoding the dopamine D2 receptor, has been extensively studied in addiction research. One variant, called the tachyia polymorphism, is associated with reduced D2 receptor density in the brain. People carrying this variant have fewer dopamine receptors available to respond to dopamine release, which might mean that natural rewards feel less satisfying. The hypothesis, still debated but supported by substantial evidence, is that these individuals might be more likely to seek out artificial ways to boost dopamine signaling, including through drug use. The DRD4 gene, encoding another dopamine receptor, has variants associated with novelty-seeking behavior and impulsivity, traits that increase risk for experimentation with drugs and progression from use to dependence. The long version of this gene, characterized by 7 repeats of a specific DNA sequence, has been linked to attention deficit hyperactivity disorder, sensation-seeking behavior, and substance use disorders, suggesting a common genetic pathway underlying these superficially different conditions. Genes involved in serotonin signaling, particularly the serotonin transporter gene SLC6A4, also affect addiction vulnerability. The short version of this gene is associated with increased anxiety and stress sensitivity, traits that can increase the appeal of substances that provide temporary relief from emotional discomfort. This exemplifies how genes don't directly cause addiction, but rather influence intermediate traits: anxiety, stress reactivity, emotional regulation capacity, that in turn affect the likelihood of developing problematic substance use. Beyond individual genes, recent research using genome-wide association studies, GWAS, has begun to reveal the true complexity of addiction genetics. These studies scan the entire genome, looking for common genetic variants associated with addiction, without requiring prior hypotheses about which specific genes might be involved. A landmark GWAS published in 2023, involving over 1 million people, identified numerous genetic variants associated with general addiction risk and with specific substance use disorders. What emerged from this research was a picture of remarkable genetic complexity. Hundreds of genetic variants, each with small effects, contribute to addiction vulnerability. Many of these variants are in genes whose connection to addiction wasn't previously suspected, highlighting how much we still have to learn. But the study also revealed something encouraging: substantial genetic overlap between different substance use disorders. The same genetic variants that increase risk for alcohol dependence also increase risk for cannabis, opioid, and nicotine dependence. This genetic overlap supports what clinicians have long observed: people with one substance use disorder are at elevated risk for developing another. The phenomenon isn't simply explained by drug culture or availability. It's partly rooted in shared genetic vulnerabilities affecting common neurobiological pathways. This also suggests that interventions targeting these common pathways might help prevent or treat multiple forms of addiction simultaneously. But genes don't operate in isolation. They interact with environmental factors in ways that profoundly influence outcomes. This is the domain of gene-environment interaction research, and it's here that the nature versus nurture debate dissolves into a more nuanced understanding of how biology and experience shape behavior. The concept is straightforward. The effect of a genetic variant depends on the environment in which it's expressed, and the effect of an environmental factor depends on an individual's genetic makeup. A variant that increases addiction risk might have minimal effect in a supportive, low-stress environment with limited drug availability, but substantial effect in a chaotic, traumatic environment with easy access to substances. The MAOA gene, encoding monoamine oxidase A, an enzyme that breaks down neurotransmitters including dopamine and serotonin, provides a striking example. One variant produces less active enzyme, resulting in higher levels of these neurotransmitters. Research has shown that boys carrying this low-activity variant who experienced childhood maltreatment were significantly more likely to develop conduct disorder, antisocial behavior, and substance use problems than boys with the same variant who didn't experience maltreatment, or than maltreated boys with the high-activity variant. The gene doesn't cause these outcomes, but it appears to modulate sensitivity to environmental adversity. This pattern, called differential susceptibility, suggests that some genetic variants don't simply increase or decrease risk, but rather make individuals more sensitive to environmental influences, for better or worse. In positive environments, these susceptibility genes might confer advantages. In negative environments, they increase vulnerability. Epigenetics adds another layer of complexity to this picture. Epigenetic modifications, chemical changes to DNA, or to the proteins around which DNA is wrapped, can alter gene expression without changing the underlying genetic code. These modifications can be triggered by environmental factors, including stress, trauma, and substance use itself. Remarkably, some epigenetic changes can be transmitted across generations, providing a mechanism by which parental or even grandparental experiences might influence offspring vulnerability. Research on epigenetics in addiction is still relatively young, but early findings are provocative. Chronic stress, for example, can cause epigenetic modifications to genes involved in stress response, potentially creating lasting changes in how the stress system functions. Substance use can trigger epigenetic modifications in reward pathway genes, potentially contributing to the long-lasting changes in motivation and reward processing that characterize addiction. The developmental timing of genetic and environmental influences also matters profoundly. The Virginia Twin Study, a longitudinal study following twins from adolescence through adulthood, revealed that the relative importance of genetic versus environmental factors changes across the lifespan. In early adolescence, initiation of substance use is strongly influenced by family and peer environment, shared environmental factors. But as individuals move into young adulthood, genetic factors become increasingly important in determining who progresses from experimentation to problematic use. This developmental shift makes sense when we consider neurobiology. During adolescence, when the reward system is highly active but the prefrontal cortex is still developing, peer influence and environmental factors heavily shape behavior. But as the brain matures and individuals have more autonomy over their choices and environments, underlying genetic vulnerabilities in reward processing, impulse control, and stress response become more evident. This has important implications for prevention and intervention. Early adolescence represents a critical window where environmental interventions, family support, peer selection, skill building can have outsized effects, potentially counteracting genetic vulnerabilities before problematic patterns become established. By young adulthood, when genetic factors are exerting stronger influence, interventions might need to be more intensive and specifically tailored to individual neurobiological profiles. The story of genetics in addiction is not one of determinism, but of probability and interaction. Genetic factors substantially influence risk, but they don't dictate destiny. Someone with high genetic vulnerability who grows up in a supportive environment, learns healthy coping skills, and avoids early exposure to substances might never develop an addiction. Someone with low genetic vulnerability who experiences significant trauma, lacks social support, and has easy access to drugs might still develop serious problems. Understanding addiction genetics serves several crucial purposes. First, it helps destigmatize the condition. When we recognize that much of addiction risk is rooted in inherited biological variation rather than moral failing, compassion becomes the scientifically justified response. Second, it points toward more personalized approaches to prevention and treatment. As genetic testing becomes more sophisticated and affordable, we might eventually be able to identify individuals at high risk and provide targeted interventions before problems develop. Third, genetic research continues to reveal the neurobiological mechanisms underlying addiction, identifying potential targets for medication development. But genetic knowledge also raises ethical challenges. How do we balance the right to know one's genetic risks against the potential for genetic discrimination in insurance or employment? How do we communicate probabilistic risk information without being either falsely reassuring or needlessly alarming? These questions don't have simple answers, but they're becoming increasingly urgent as genetic science advances. What's clear is that the genetic component of addiction is substantial, complex, and interactive. It involves hundreds of genetic variants, each contributing small effects, operating through multiple biological pathways, interacting with environmental factors across the lifespan. The human genome doesn't contain a single addiction gene waiting to be discovered, but it does contain a wealth of information about individual vulnerability, information that, properly understood and applied, could transform how we prevent and treat these disorders. Substance addictions, deep dive, chemical dependencies. While all addictive substances ultimately engage the brain's reward circuitry, each class of drugs accomplishes this through distinct neurochemical mechanisms, produces characteristic patterns of use, and creates specific challenges for treatment. Understanding these differences is crucial because addiction is not a monolithic entity. It's a family of related disorders, each with unique features deserving targeted attention. Alcohol stands as one of the oldest and most widely used psychoactive substances in human history. Archaeological evidence suggests humans have been fermenting and consuming alcohol for at least 10,000 years. Today, alcohol use disorder affects approximately 15 million people in the United States alone, making it one of the most prevalent substance use disorders. Yet its ubiquity and legal status often lead to underestimation of its addictive potential and dangers. Alcohol's effects on the brain are promiscuous. Unlike drugs that target a single receptor system, alcohol affects multiple neurotransmitter systems simultaneously. It enhances the activity of GABA, the brain's primary inhibitory neurotransmitter, producing the characteristic relaxation and loss of inhibition associated with drinking. It inhibits glutamate, the primary excitatory neurotransmitter, further dampening neural activity. It triggers release of endogenous opioids and increases dopamine in reward pathways. This multisystem action explains alcohol's complex subjective effects and its broad impact on cognition, emotion, and behavior. Chronic alcohol exposure forces the brain into a series of compensatory adaptations. GABA receptors downregulate, glutamate receptors upregulate, and neuronal excitability increases in an attempt to maintain normal function despite alcohol's depressant effects. This neuroadaptation is why tolerance develops. More alcohol is needed to produce the same effects. But these adaptations create a problem when drinking stops. With GABA activity artificially suppressed and glutamate activity artificially enhanced, the sudden absence of alcohol leaves the brain in a state of hyperexcitability. This is alcohol withdrawal, and in severe cases, it can be medically dangerous. Symptoms range from tremor, anxiety, and insomnia. In mild cases, to seizures and delirium tremens in severe cases. Alcohol and benzodiazepines are the only common substances whose withdrawal can be life-threatening, a fact that underscores the profound neurochemical dependence chronic alcohol use creates. The psychological effects of alcohol extend beyond intoxication and withdrawal. Chronic heavy drinking is associated with significant cognitive impairment, affecting memory, executive function, and decision-making. The prefrontal cortex, which we've discussed as crucial for impulse control and planning, shows particular vulnerability to alcohol's toxic effects. Brain imaging studies reveal reduced gray matter volume in the prefrontal cortex of people with alcohol use disorder, corresponding with impairments in judgment and self-control. Yet here's something remarkable. Much of this damage is reversible with sustained abstinence. Studies following people in recovery from alcohol use disorder have documented gradual restoration of brain volume and improvement in cognitive function over months to years. The brain's capacity for healing, even after prolonged alcohol exposure, is far greater than once believed. Opioids represent a different category of addictive substances, though tragically, they've dominated recent addiction-related mortality statistics. The opioid crisis, as it's been called, has evolved through several waves. It began in the late 1990s with overprescription of opioid pain medications, progressed through rising heroin use as pills became harder to obtain, and has most recently been driven by illicitly manufactured fentanyl, a synthetic opioid 50 to 100 times more potent than morphine. Opioids work by binding to mu-opioid receptors throughout the brain and body. These receptors are part of the endogenous opioid system, which normally helps regulate pain, reward, and stress. When opioids bind to these receptors, they trigger powerful effects: intense euphoria, pain relief, and a profound sense of well-being and contentment. This isn't a subtle high. At sufficient doses, opioids can produce feelings of such intense pleasure and peace that users sometimes describe it as better than any natural experience. The problem is that this extraordinary effect comes with extraordinary neurological consequences. Opioid receptors regulate numerous physiological functions, including breathing. High doses suppress respiratory drive, which is how opioid overdoses kill. People simply stop breathing. The narrow therapeutic window between a dose that produces desired effects and one that stops respiration makes opioids inherently dangerous. Chronic opioid use produces profound physical dependence. The body adapts to constant opioid receptor stimulation by reducing its production of endogenous opioids and decreasing receptor sensitivity. Within days to weeks of regular use, trying to stop precipitates withdrawal, a syndrome so physically and psychologically uncomfortable that many users describe it as unbearable. Opioid withdrawal includes severe flu-like symptoms, muscle aches, sweating, runny nose, gastrointestinal distress. But the psychological symptoms often drive relapse even more powerfully than physical discomfort: intense anxiety, depression, and a complete absence of motivation or pleasure. While opioid withdrawal isn't medically dangerous in most cases, it's intensely aversive, creating powerful negative reinforcement for continued use. The treatment landscape for opioid use disorder has evolved significantly in recent decades. Medication-assisted treatment, using medications like methadone, buprenorphine, or naltrexone, has become the gold standard. These medications work by occupying opioid receptors, either providing a subtle, less euphoric stimulation, methadone, buprenorphine, or blocking them entirely, naltrexone. Research consistently shows that medication-assisted treatment produces better outcomes than behavioral interventions alone, yet access remains limited and stigma persists even among addiction treatment providers. Stimulants, including cocaine, methamphetamine, and prescription medications like Adderall, represent another major class of addictive substances. Unlike alcohol's multi-system effects or opioids' receptor-specific action, stimulants primarily target the dopamine system directly. Cocaine blocks the dopamine transporter, preventing dopamine reuptake and causing it to accumulate in the synapse. Methamphetamine not only blocks reuptake, but also causes dopamine release and enters neurons to trigger additional dopamine release from storage sites. The result is a massive, sustained elevation in dopamine, far beyond what the reward system ever encounters naturally. This produces the characteristic stimulant high, intense euphoria, heightened energy and alertness, inflated self-confidence, and decreased need for sleep or food. Users often describe feeling invincible, capable of anything, focused with laser-like intensity. But this comes at a severe neurobiological cost. The massive dopamine surge is followed by proportionate depletion. As dopamine levels crash, users experience profound dysphoria, fatigue, and anhedonia, the inability to experience pleasure. This crash is so aversive that many users immediately seek another dose, leading to characteristic binge patterns, where someone might use repeatedly over days before finally collapsing from exhaustion. Chronic stimulant use produces neurotoxicity, actual damage to dopamine neurons. Brain imaging studies show reduced dopamine transporter density in the brains of chronic methamphetamine users, indicating loss of dopamine nerve terminals. This damage corresponds with cognitive impairments, particularly in executive function, decision-making, and impulse control. Unlike the reversible changes seen with alcohol, some stimulant-induced damage may be permanent, though substantial recovery can occur with prolonged abstinence. Stimulant withdrawal is primarily psychological rather than physical. There's intense craving, profound depression, and sometimes paranoid or psychotic symptoms. Sleep disturbances can persist for weeks or months. The absence of significant physical withdrawal might make stimulant addiction seem less serious than opioid addiction, but this is misleading. The psychological dependence can be equally powerful, and relapse rates are comparable or higher. Treatment for stimulant use disorders has been challenging because, unlike opioids or alcohol, there are no FDA-approved medications specifically for stimulant addiction. Treatment relies heavily on behavioral interventions, particularly cognitive behavioral therapy and contingency management, which uses positive reinforcement to promote abstinence. Recent research on medications for stimulant addiction has shown some promise, particularly combinations targeting multiple neurotransmitter systems, but effective pharmacological treatments remain elusive. Cannabis occupies a complex and evolving place in discussions of addiction. As legalization expands, attitudes have shifted toward viewing cannabis as relatively harmless. While it's true that cannabis is less acutely toxic than opioids, alcohol, or stimulants, and physical dependence is less severe, cannabis use disorder is a real phenomenon affecting approximately 4 million Americans. Cannabis works primarily through the endocannabinoid system, targeting CB1 receptors throughout the brain. This system normally helps regulate reward, memory, pain, and numerous other functions. THC, the primary psychoactive component of cannabis, binds to these receptors, producing effects ranging from euphoria and relaxation to perceptual alterations and sometimes anxiety or paranoia. The endocannabinoid system interacts intimately with the dopamine system, and cannabis does trigger dopamine release in reward pathways, though more modestly than stimulants or opioids. What makes cannabis addiction insidious is that it's often subtle. People might not recognize their use as problematic until they try to quit and realize how difficult it is. Cannabis withdrawal, while milder than opioid or alcohol withdrawal, is real and can be surprisingly uncomfortable. Irritability, anxiety, sleep disturbances, decreased appetite, and intense cravings. These symptoms peak around the third day of abstinence and can persist for weeks, creating a significant barrier to quitting for regular users. Of particular concern is cannabis use during adolescence, when the brain is still developing. Research suggests that regular cannabis use during this critical period may have lasting effects on cognitive function, particularly memory and executive function. The question of whether these effects are permanent or reversible with sustained abstinence is still being investigated, with evidence pointing in both directions. Nicotine, delivered primarily through tobacco products but increasingly through e-cigarettes, is remarkable for being simultaneously one of the most addictive and least intoxicating substances. Nicotine produces relatively subtle subjective effects: a mild rush, increased alertness, and reduced stress or anxiety. Yet its addictive potential is extraordinary. Studies suggest that among people who use nicotine regularly, approximately 32% will develop dependence, a rate comparable to or exceeding that of many illegal drugs. Nicotine's addictive power comes from its rapid delivery to the brain. Cigarette smoking gets nicotine to the brain in about 10 seconds. Its short half-life, creating frequent opportunities for reinforcement, and its effects on nicotinic acetylcholine receptors that modulate dopamine release. Chronic nicotine use leads to upregulation of these receptors, creating both tolerance and withdrawal symptoms upon cessation. Nicotine withdrawal includes irritability, anxiety, difficulty concentrating, increased appetite, and intense cravings. While not medically dangerous, these symptoms are uncomfortable enough to drive relapse in approximately 95% of quit attempts without treatment. Fortunately, effective treatments exist. Nicotine replacement therapy, bupropion, and varenicline all increase quit rates significantly, and combining medication with behavioral support produces the best outcomes. Each of these substance categories, alcohol, opioids, stimulants, cannabis, nicotine, represents a distinct challenge with unique neurobiological mechanisms, characteristic use patterns, and specific treatment considerations. Yet they share common features. All activate reward pathways, all produce neuroadaptations that maintain use despite negative consequences, all create a cycle of use and withdrawal that becomes self-perpetuating. Understanding these commonalities while appreciating the distinctions is essential for effective treatment. A one-size-fits-all approach fails to address the specific neurochemical disruptions each substance creates. Effective treatment requires not only understanding addiction as a general phenomenon, but also understanding how alcohol dependence differs from opioid dependence, how stimulant addiction differs from cannabis use disorder. The ultimate tragedy of substance addiction is how something that begins as a choice, a decision to try a substance, often made in adolescence or young adulthood, gradually transforms into a condition that erodes choice itself. The substances don't change, but the brain does, in ways that make continued use feel necessary rather than optional. Recognizing this transformation as a medical condition rather than a moral failing is crucial for approaching these disorders with both the seriousness and the compassion they deserve. Behavioral addictions, when actions become compulsions. The recognition that behaviors, not just substances, can become addictive represents one of the most important developments in addiction psychology over the past 3 decades. In 2013, the American Psychiatric Association took a landmark step by reclassifying pathological gambling as gambling disorder and placing it in a new category: substance-related and addictive disorders. This was the first time a behavioral addiction received the same diagnostic status as a substance addictions, reflecting mounting evidence that the two share fundamental neurobiological mechanisms. The story of gambling disorder illuminates why this reclassification was warranted. Gambling, in various forms, has existed throughout human history. Dice games in ancient Rome, card games in medieval Europe, betting on sporting events across cultures. For most people who gamble, it's occasional entertainment with controlled risk. But for approximately 1% of adults, gambling escalates into a pattern that meets criteria for addiction: continued engagement. Despite severe negative consequences, loss of control over the behavior, withdrawal symptoms when stopping, and progressive escalation in the amount of time and money invested. What makes gambling addictive isn't the specific activity, but the neuropsychological process it engages. When someone places a bet, their brain makes a prediction about the outcome. This prediction generates anticipatory dopamine release, not when they win, but during the moment of uncertainty between placing the bet and learning the result. The unpredictability is key. If outcomes were perfectly predictable, dopamine wouldn't surge. It's the uncertainty, the possibility of winning without certainty, that drives the dopamine response. This is why variable ratio reinforcement schedules, where rewards come after an unpredictable number of responses, are so powerful in creating persistent behavior. Psychologist B.F. Skinner demonstrated this in the 1950s with rats and pigeons, showing that animals will respond far more persistently for rewards delivered on variable schedules than for rewards delivered consistently. Gambling represents the perfect variable ratio schedule. You never know when the next win will come, but you know it could be the very next bet. Brain imaging studies of people with gambling disorder reveal striking similarities to substance use disorders. They show reduced activity in prefrontal regions involved in impulse control and decision-making. They show heightened activation in reward circuits when viewing gambling cues. They show altered dopamine receptor density in the striatum. These aren't subtle similarities. They're fundamental neurobiological parallels, suggesting that gambling disorder and substance addictions may be, at their core, variations of the same underlying condition. The psychological features of gambling disorder also mirror substance addictions. There's tolerance, needing to gamble with larger amounts of money to achieve the desired excitement. There's withdrawal, feeling restless or irritable when attempting to stop. There's loss of control, repeated unsuccessful efforts to cut back. There's continued engagement despite negative consequences, persisting even after devastating financial, occupational, or relationship losses. One particularly tragic feature of gambling disorder is the phenomenon of chasing losses. After losing money, gamblers often increase their betting in an attempt to win back what they've lost. This behavior, irrational from an economic perspective, makes perfect sense neurobiologically. Losses trigger negative prediction errors. The outcome was worse than expected, which motivates behavior aimed at rectifying the error. The gambler's brain is essentially trying to solve a problem, not recognizing that continued gambling only deepens the hole. Gaming disorder represents a newer addition to recognized behavioral addictions, officially added to the International Classification of Diseases, ICD-11, by the World Health Organization in 2018, though not yet included in the DSM-5 as a formal diagnosis. The classification remains somewhat controversial, with debates centering on whether problematic gaming represents a distinct disorder or a symptom of underlying conditions like depression or social anxiety. However, research supporting gaming disorder as a distinct condition has accumulated rapidly. Brain imaging studies show similarities to substance use disorders: heightened reward system, activation when anticipating gaming, reduced prefrontal control, and altered dopamine signaling. Longitudinal studies demonstrate that problematic gaming can predict later problems independent of pre-existing mental health issues, suggesting it's not merely secondary to other conditions. What makes gaming potentially addictive? Modern video games, particularly online multiplayer games, incorporate numerous psychological mechanisms that engage reward and motivation systems. There's immediate feedback. Actions produce instant, visible results. There's social connection. Playing with or against others activates social reward systems. There's progression. Leveling up, unlocking achievements, advancing through the game creates ongoing goals. There's variable reward. Loot boxes, random drops, unexpected wins mirror gambling's unpredictability. Some games also employ what's called a Skinner box design, named after the psychologist who pioneered operant conditioning research. These games require repetitive actions that are intermittently rewarded, creating persistent engagement. Mobile games have particularly embraced this design, often incorporating mechanisms like daily login bonuses, limited time events, and energy systems that encourage frequent, repeated engagement throughout the day. The social dimension of gaming can make it especially compelling. Massively multiplayer online games create persistent worlds where friendships form, where leaving means letting down teammates, where status and identity become bound up with the game. For some people, particularly those who feel socially marginalized or awkward in face-to-face interactions, online gaming communities provide a sense of belonging they struggle to find elsewhere. Internet use disorder, while not formally recognized in the DSM-5, is increasingly studied as a potential behavioral addiction. The internet provides access to virtually limitless content, immediate gratification of curiosity or boredom, and connection with others. Its very breadth, offering everything from information to social interaction to entertainment to shopping, makes it difficult to define what internet addiction even means. Are we talking about excessive social media use, compulsive news reading, online shopping, or pornography use? Recent research suggests it might be more productive to consider specific problematic behaviors facilitated by the internet, rather than internet use itself as addictive. Social media addiction, for instance, shows distinct features: compulsive checking, strong emotional responses to notifications, anxiety when unable to access platforms, and interference with offline activities. These behaviors activate reward systems through mechanisms we'll explore in depth in the next section. Shopping addiction, or compulsive buying disorder, involves repetitive, excessive shopping that causes distress or impairment. While anyone might occasionally overspend, compulsive buyers experience intense urges to purchase, temporary euphoria during shopping, and subsequent guilt or regret, a cycle remarkably similar to substance use. Brain imaging studies, though limited, suggest abnormalities in impulse control circuits and enhanced reward sensitivity. What unites these diverse behavioral addictions is their engagement of the same reward and motivation systems vulnerable to substance addictions. They don't introduce external chemicals, but they don't need to. By providing unpredictable rewards, by offering escape from uncomfortable feelings, by creating social connections, by generating progression and achievement, they naturally activate dopamine pathways and create learned associations that can become compulsive. The opponent process theory, originally developed to explain substance addiction, applies equally well to behavioral addictions. Initial engagement produces positive feelings, the AA process. With repeated engagement, an opposing negative feeling emerges when not engaging in the behavior. the B process. Over time, the motivation shifts from seeking pleasure to avoiding the discomfort that's emerged in the behavior's absence. The gambler isn't just chasing wins, they're avoiding the anxiety and restlessness that builds when not gambling. The gamer isn't just enjoying the game, they're escaping the dysphoria that emerges when logged off. Treatment approaches for behavioral addictions draw heavily from substance addiction treatment, but with important modifications. Total abstinence, the goal for most substance addictions, isn't always necessary or even desirable for behavioral addictions. Most people need to use the internet for work or communication. Gaming can be part of a healthy, balanced life. The goal is often controlled, moderate engagement rather than complete cessation, what's sometimes called harm reduction rather than abstinence. Cognitive behavioral therapy for behavioral addictions focuses on identifying triggers, developing alternative coping strategies, and gradually building a life with sources of meaning and pleasure beyond the problematic behavior. For gambling disorder specifically, cognitive therapy addresses erroneous beliefs about odds, luck, and control that maintain gambling behavior. For gaming, it might focus on building offline social connections and developing skills for managing the anxiety or depression that gaming was masking. Medication can play a role, though no drugs are specifically approved for behavioral addictions. Naltrexone, an opioid antagonist, has shown some efficacy for gambling disorder, possibly by blunting the reward system's response to winning. Antidepressants can help when underlying depression or anxiety is contributing to the problematic behavior. But medication is typically considered adjunctive to behavioral treatment rather than a primary intervention. One crucial insight from behavioral addiction research is that the capacity for addiction isn't about specific substances. It's about how reward systems interact with learning systems to create compelling patterns of behavior. This understanding expands our conception of addiction beyond pharmacology into psychology, neuroscience, and even technology design. It also raises important questions about responsibility. If game developers or gambling operators design products specifically to exploit reward systems and create addictive engagement, what ethical obligations do they have? Should there be regulations on game design similar to regulations on substances? These questions, which would have seemed bizarre 2 decades ago, are increasingly relevant as we understand that addiction isn't fundamentally about drugs. It's about how certain stimuli, whether chemical or behavioral, interact with vulnerable brains. The recognition of behavioral addictions has also helped reduce stigma around substance addictions. If people can become addicted to gambling or gaming, activities that don't involve putting substances into the body, it becomes harder to maintain that substance addiction is simply a moral failing. Both reflect the same underlying vulnerability. A reward system that, under certain conditions, can learn patterns so compelling they override conscious judgment. Yet this recognition also expands the landscape of what we need to be concerned about. If behaviors can be addictive, then virtually anything that activates reward systems becomes potentially problematic for vulnerable individuals. This doesn't mean we should panic about every pleasurable activity, but it does suggest we need to think carefully about how we design technologies and environments, particularly for developing brains that may be especially vulnerable to addictive patterns. Digital age dependencies, the screen's magnetic pull. If substance addictions represent ancient vulnerabilities exploited by modern chemistry, and behavioral addictions represent timeless patterns given new forms, then digital addictions represent something unprecedented. Evolutionary ancient reward systems confronting stimuli that have existed for only a tiny fraction of human history, designed with unprecedented sophistication to capture and hold attention. The smartphone you carry represents one of the most concentrated sources of addictive potential ever created. It provides instant access to social connection, infinite information, compelling entertainment, and countless other rewards. It does so through an interface optimized over billions of human hours to be as engaging as possible. And it's available 24 hours a day, generating notifications specifically designed to interrupt whatever you're doing and draw you back. The numbers are striking. The average person checks their smartphone approximately 58 times per day. Nearly half of those checks occur within 3 minutes of the previous check. Estimates suggest people spend between 3 and 4 hours daily on their phones, with much of that time on social media platforms. These aren't necessarily signs of addiction. Many people use technology in balanced, healthy ways. But the ubiquity and intensity of smartphone use has created a population-level vulnerability that we're only beginning to understand. Social media platforms, in particular, have become a focus of addiction research and concern. They combine several potent psychological mechanisms in one package: social validation, variable rewards, infinite content, fear of missing out, and comparison dynamics. Each of these deserves examination. Social validation represents one of our deepest psychological needs. Throughout human evolution, acceptance by our social group meant survival, rejection meant death. Our brains evolved exquisite sensitivity to social signals: approval, disapproval, inclusion, exclusion. Social media platforms tap directly into this sensitivity by quantifying social approval. Every like, comment, share, and follower becomes a measurable unit of social validation. This quantification does something interesting to our brains. Research shows that receiving social media likes activates the same reward circuits, the nucleus accumbens and ventral tegmental area, activated by food, sex, and drugs. The neuroimaging patterns are remarkably similar. This isn't metaphorical. Social media engagement literally triggers the same reward pathways that evolved to reinforce survival-critical behaviors. But social media engagement doesn't just trigger reward pathways randomly. It does so on variable schedules. When you post something, you don't know if you'll get 0 likes or 1,000. When you refresh your feed, you don't know if you'll see something funny, something enraging, something boring, or something surprising. This unpredictability creates the same effect as a slot machine or variable ratio reinforcement in gambling: persistent, resistant to extinction behavior. B.F. Skinner's pigeons would peck a key thousands of times for uncertain rewards delivered on variable schedules. Humans pull down to refresh social media feeds for the same fundamental reason. Each refresh is a potential reward, and the uncertainty makes it compelling. The fact that most refreshes produce nothing particularly interesting doesn't diminish the behavior. It enhances it, because the occasional surprising or rewarding post is all the reinforcement the learning system needs. Social media platforms employ algorithms designed to maximize engagement, to keep you scrolling, checking, and posting as long as possible. These algorithms aren't neutral. They learn what keeps your attention and show you more of it. They time notifications for maximum impact. They create endless feeds that remove natural stopping points. They employ dozens of psychological techniques refined through massive data collection and A/B testing to make their platforms as compelling as possible. This isn't conspiracy theory. It's explicit business model. Social media platforms make money by selling advertising, and advertising revenue depends on user engagement. The more time users spend on the platform, the more valuable the platform is to advertisers. Platform designers aren't necessarily trying to create addiction, but they are trying to maximize engagement, and the techniques that maximize engagement overlap considerably with the mechanisms that create addictive behavior. The fear of missing out, or FOMO, represents a particularly powerful psychological lever. human beings are naturally averse to the possibility that something interesting, important, or pleasurable is happening without them. This aversion has evolutionary roots. Missing crucial social information could have serious consequences for our ancestors. But social media creates the impression that interesting things are always happening, that exciting experiences are constantly unfolding, that social connections are being made and deepened without you if you're not online. This creates a state of ambient anxiety about being disconnected. Studies have found that people experience genuine stress when separated from their smartphones, even for short periods. The inability to check social media produces measurable physiological arousal, elevated heart rate, increased cortisol, and reports of discomfort. This mirrors drug withdrawal in important ways. Separation from the stimulus produces negative affective states that motivate returning to the stimulus. The dopamine cycle of social media use looks something like this. You feel bored, lonely, or anxious. You check your phone, hoping for something interesting or validating. You scroll through feeds, occasionally finding something that produces a small dopamine hit, a funny post, a like on something you shared, a message from a friend. This temporarily relieves the negative feeling, but the relief is brief, and the baseline negative feeling returns, often slightly amplified. So you check again, and again. This cycle can become self-perpetuating. The constant checking trains the brain to expect frequent small rewards, making their absence feel increasingly uncomfortable. The brief dopamine hits during checking feel good in the moment, but don't provide lasting satisfaction. The comparison dynamics of social media, seeing others' curated highlights while experiencing your own mundane reality, can actually decrease life satisfaction, creating more negative effect that you then try to escape through more social media use. Neurobiological research on social media addiction is still relatively new, but initial findings are concerning. Studies have found alterations in brain structure and function among heavy social media users that parallel changes seen in substance and behavioral addictions. Reduced gray matter in regions involved in decision-making and impulse control, altered activation in reward circuits when viewing social media-related cues, and evidence of tolerance-like effects where increasing amounts of social media use are needed to achieve the same subjective effects. One particularly striking study used positron emission tomography to examine dopamine synthesis capacity in relation to smartphone social behavior. Researchers found that people who spent more time on social apps showed lower dopamine synthesis capacity in the putamen, a region of the striatum involved in habit formation and reward processing. This suggests that heavy social media use might actually be altering fundamental reward system function. The adolescent brain's particular vulnerability to social media cannot be overstated. Adolescence is characterized by heightened sensitivity to social rewards and peer evaluation, combined with incomplete prefrontal development that would normally provide impulse control and perspective taking. For teenagers, social media combines maximum reward, peer approval, social connection, with minimum protection, limited ability to regulate usage or maintain perspective. This creates a neurobiological perfect storm. The teenage brain is wired to care intensely about peer evaluation, and social media provides real-time, quantified feedback on that evaluation. The developing prefrontal cortex struggles to maintain boundaries around usage or critically evaluate whether online social dynamics reflect reality. The reward system is highly sensitive, making social media's variable rewards particularly compelling. Longitudinal studies following adolescents over time have found associations between heavy social media use and various mental health problems, increased anxiety and depression, sleep disturbances, attention difficulties, and lower life satisfaction. The causal direction isn't entirely clear. Does social media use cause these problems, Or do adolescents with these problems use social media more heavily? Likely both occur, creating a vicious cycle where mental health problems drive social media use, which exacerbates mental health problems. Smartphones add another layer to digital addiction by making the addictive content not just available, but omnipresent. Previous forms of media, even highly engaging ones like television, had natural boundaries. They required being in a specific place, turning on a specific device. Smartphones eliminate these boundaries. The possibility of social media engagement, gaming, news, or whatever else someone finds compelling is always present, always accessible within seconds. This constant accessibility interacts with our brain's attentional systems in problematic ways. Studies of smartphone use have found that the mere presence of one's phone, even if it's turned off and face down, reduces available cognitive capacity for other tasks. The brain appears to be allocating some processing resources to not checking the phone, resources that would otherwise be available for whatever task is at hand. This creates a kind of constant, low-level cognitive drain that many smartphone users don't consciously notice, but that accumulates over time. Notifications represent a particularly pernicious feature of smartphone design. Each notification, a buzz, a ding, a flash of light, represents a potential reward. Your brain learns that these signals might indicate something important, interesting, or pleasant. Even when most notifications are trivial, the occasional important one is enough to maintain the learned association. Notifications essentially train us to respond to external stimuli like Pavlov's dogs, interrupting whatever we're doing to check what might be waiting. The design of these notifications isn't accidental. Variable notification timing, the strategic use of red notification badges, red triggers attention and urgency, the specific sounds chosen, all of these are optimized through research and testing to capture attention. Tech companies employ human attention as a resource to be captured and held, and they've developed highly sophisticated tools for doing so. Screen addiction, whether to social media, gaming, or other digital content, shares many features with substance and behavioral addictions. There's compulsive use despite negative consequences. There's loss of control, with usage regularly exceeding intended amounts. There's withdrawal, with negative mood states when unable to access screens. There's tolerance, with increasing amounts of screen time needed to feel satisfied. There's social and occupational impairment, with digital use interfering with relationships, work, or other responsibilities. But screen addictions also have unique features that complicate treatment. Unlike substance addictions, where abstinence is a clear goal, most people need some level of digital engagement for work, education, or basic social functioning. Drawing the line between healthy, necessary use and problematic, addictive use is genuinely difficult. Is 3 hours on social media per day excessive? What about 5? How do we count time that's mostly scrolling mindlessly versus time actively engaging with content? Treatment approaches for problematic digital use are still evolving, but several strategies show promise. Digital detoxes, periods of complete abstinence from social media or smartphones, can help reset reward system sensitivity and break automatic checking habits. Setting specific boundaries around when and where digital use is allowed can create structure that impulsive use undermines. Using apps that track and limit screen time provides awareness and accountability. Identifying what psychological needs digital use is meeting and finding healthier ways to meet those needs addresses underlying motivations. At a broader level, addressing digital addiction requires thinking about how we design technology, regulate platforms, and educate users, particularly young people. Should social media platforms be required to include features that limit addictive design? Should there be age restrictions on certain features like infinite scroll or notification systems? How do we balance the genuine benefits of digital connection against the risks of addictive engagement? These are not simple questions, and they don't have simple answers. But they're becoming increasingly urgent as we recognize that our ancient brains, evolved for a world that no longer exists, are encountering stimuli specifically designed to capture and hold attention, often in ways that exploit rather than serve our well-being. Psychological frameworks, models of understanding. While neuroscience has revealed the biological mechanisms underlying addiction, psychology provides frameworks for understanding how individual experiences, thoughts, and environmental factors interact with neurobiology to produce addictive patterns. These psychological models don't contradict neurobiological explanations. They complement them, describing different levels of analysis of the same phenomenon. The biopsychosocial model, proposed by psychiatrist George Engel in 1977 and later adapted specifically for addiction, represents the most comprehensive framework for understanding substance use disorders. This model rejects reductionist approaches, the idea that addiction can be fully explained by either biology alone, psychology alone, or social factors alone. Instead, it proposes that addiction emerges from complex interactions among all three domains, with each level influencing the others in recursive feedback loops. The biological component includes genetic vulnerability, neurochemical imbalances, physical health, and the direct pharmacological effects of substances or the neurological impacts of behaviors. This is the level at which genes influence receptor sensitivity, where chronic drug use alters reward circuit function, where withdrawal symptoms manifest. But biology doesn't operate in a vacuum. The psychological component includes cognition, emotion regulation, personality traits, mental health conditions, coping mechanisms, and past experiences. How a person thinks about their substance use, what emotional needs it serves, what other mental health struggles they're managing. These psychological factors profoundly influence whether vulnerability transforms into problematic use. Consider two people with similar genetic vulnerability to alcohol dependence. One develops strong coping skills, effective emotional regulation, and a sense of meaning and purpose through work and relationships. The other experiences chronic anxiety, never learns effective stress management, and turns to alcohol for relief. Their shared genetic vulnerability manifests very differently depending on psychological factors. The social component encompasses family dynamics, peer influences, socioeconomic status, culture, availability of substances, social support systems, and broader policy and legal contexts. Using the same example, one person grows up in a supportive family with strong boundaries around substance use, while the other grows up with parental addiction and easy access to alcohol. One lives in a community with extensive social services and treatment options. The other in a community with minimal support. The genius of the biopsychosocial model is recognizing that these levels are not independent. They constantly interact. Genetic vulnerability influences which psychological coping strategies feel necessary or effective. Psychological stress alters biological stress response systems. Social circumstances shape both which biological vulnerabilities get expressed and which psychological resources are available. Treating addiction effectively requires addressing all three levels simultaneously. The disease model of addiction, while somewhat controversial, has been instrumental in reducing stigma and improving access to treatment. This model, articulated most clearly by researchers like Alan Leshner in the 1990s, characterizes addiction as a chronic brain disease, analogous to conditions like diabetes or hypertension. Like these conditions, addiction has biological underpinnings, requires medical treatment, and needs ongoing management even after acute symptoms resolve. The disease model emphasizes several key points. Addiction is not simply a choice or a moral failing. It involves changes in brain structure and function. It's chronic and relapsing in nature. It requires medical intervention, and recovery is possible, but requires professional support. This framework has been crucial for insurance coverage of addiction treatment, for developing medication-assisted treatments, and for challenging the notion that people with addictions simply lack willpower. However, the disease model has also faced criticism. Some argue it's overly deterministic, implying people with addictions have no agency or responsibility. Others contend it medicalizes what are fundamentally social problems, deflecting attention from social determinants of addiction like poverty, trauma, and lack of opportunity. Still others worry that characterizing addiction as a brain disease can paradoxically increase stigma by marking people as neurologically damaged. These criticisms have merit, which is why most contemporary approaches combine disease model insights with recognition of social and psychological factors, essentially integrating the disease model into the broader biopsychosocial framework. Addiction involves real neurobiological changes that constitute a medical condition, but it's also influenced by personal choices, social circumstances, and psychological factors. Both perspectives are true simultaneously. The opponent process theory, developed by psychologist Richard Solomon in 1974, provides a compelling psychological model for how addiction develops over time. The theory proposes that every affective state triggers an opposing affective state, a kind of homeostatic correction. When you experience pleasure, the ore process, your brain automatically initiates a process to return to baseline, the B process. Initially, the B process is weak and delayed, so the pleasure dominates. But with repeated exposure, the B process strengthens and occurs more quickly. Applied to addiction, this explains several phenomena. The first few times someone uses a drug, the euphoric A process is strong and the negative B process is weak. They get high and then return relatively smoothly to baseline. But with continued use, the B process, withdrawal and dysphoria, becomes stronger and occurs more quickly. Eventually, much of the motivation for use is not to achieve the positive A process, but to avoid or alleviate the negative B process. This shift from positive to negative reinforcement is central to addiction trajectories. Early use is motivated by seeking pleasure. Later use is motivated by avoiding the discomfort that emerges when not using. This explains why someone can continue using despite claiming they no longer enjoy it. They're not chasing a high, they're fleeing withdrawal. The incentive sensitization theory, proposed by Terry Robinson and Kent Berridge in the early 1990s, offers another psychological perspective grounded in neuroscience. This theory distinguishes between liking, the pleasure derived from a reward, and wanting, the motivation to obtain it. The theory proposes that in addiction, the dopamine system becomes sensitized specifically to drug-related cues, creating pathological wanting even when liking has diminished. In practical terms, this means that cues associated with drug use, people, places, paraphernalia, emotional states, trigger intense cravings that can persist long into recovery. The person might consciously recognize that using won't be particularly pleasurable, that it will likely lead to negative consequences, but the sensitized wanting system creates motivation so powerful it can override rational judgment. This helps explain the seemingly irrational behavior of someone who repeatedly relapses despite genuine desire to quit. Cognitive behavioral models of addiction focus on learned associations, thought patterns, and belief systems that maintain addictive behavior. These models emphasize that addiction involves maladaptive learning. Associations between cues and drug effects become so strong they drive behavior automatically. Cognitive distortions, irrational beliefs about substances, their effects, and one's ability to control use support continued use. For example, someone might hold beliefs like, "I need alcohol to socialize," or "I can't handle stress without using," or "one drink won't hurt." These beliefs, often developed through experience and reinforced through repeated use, shape behavior in powerful ways. Cognitive behavioral therapy targets these beliefs directly, helping people identify distorted thinking patterns, challenge irrational beliefs, and develop new, healthier cognitions that support recovery. The self-medication hypothesis proposes that substance use often begins and is maintained as an attempt to manage underlying psychological distress, particularly trauma-related symptoms, anxiety, or depression. From this perspective, addiction is less about seeking pleasure and more about seeking relief from emotional pain. The substance or behavior becomes a dysfunctional coping mechanism, addressing symptoms in the short term but creating larger problems long term. Research strongly supports this framework. Studies consistently find high rates of comorbidity between substance use disorders and mental health conditions. The adverse childhood. Experiences study demonstrated powerful dose-response relationships between childhood trauma and later substance use. Many people with addictions report that substances initially provided relief from difficult emotions or memories that they didn't have other tools to manage. This has important treatment implications. If addiction is partly self-medication, then effective treatment must address the underlying distress being medicated. Treating only the substance use while ignoring trauma, anxiety, or depression is unlikely to succeed long-term because the person will still need ways to manage these conditions. Integrated treatment, addressing both substance use and co-occurring mental health conditions simultaneously, produces better outcomes than treating either condition in isolation. The social learning model emphasizes that much substance use behavior is learned through observation, modeling, and social reinforcement. Young people learn about substances and their effects partly through watching parents, siblings, peers, and media portrayals. They learn social norms around use, expectations about effects, and behaviors associated with use. The peers they choose, the environments they're in, and the cultural context all shape patterns of use. This model doesn't deny biological vulnerability or neurological changes, but it emphasizes that these operate within social contexts that powerfully influence whether vulnerability becomes problematic use. Interventions targeting social learning might focus on providing alternative role models, changing peer networks, addressing family dynamics that support use, or working with communities to change social norms. The trans-theoretical model of change, developed by Prochaska and Di Clemente, provides a framework for understanding the process of behavior change, including recovery from addiction. This model proposes that change happens through stages: pre-contemplation, not considering change; contemplation, considering change but ambivalent; preparation, planning change; action, actively changing behavior; and maintenance, sustaining change over time. Understanding these stages helps treatment providers match interventions to where someone is in their change process. Someone in pre-contemplation who doesn't yet see their use as problematic isn't ready for action-focused interventions. They need interventions that raise awareness and create motivation. Motivational interviewing is particularly suited to this stage. Someone in action stage needs practical skills and support for implementing change. Cognitive behavioral therapy and relapse prevention fit here. The trauma-informed model recognizes that trauma, particularly early childhood trauma, is both a risk factor for addiction and often a maintaining factor. This model proposes that understanding someone's trauma history is essential for effective treatment, and that treatment must create conditions of safety, trustworthiness, collaboration, empowerment, and cultural sensitivity that allow trauma survivors to heal. Trauma-informed care doesn't necessarily mean directly addressing trauma in addiction treatment. Sometimes that's clinically contraindicated during early recovery. But it does mean recognizing that behaviors that look like treatment resistance might be trauma responses, that punitive approaches are likely to re-traumatize, and that building safety and trust are prerequisites for effective intervention. These diverse psychological models aren't mutually exclusive. They describe different aspects of addiction's complexity. The biopsychosocial model provides an overarching framework recognizing multiple interacting factors. The disease model emphasizes neurological changes and medical treatment needs. Opponent process theory describes how motivation shifts over time. Incentive sensitization explains cue-triggered cravings. Cognitive behavioral models address learned patterns and thought distortions. Self-medication highlights underlying distress. Social learning emphasizes environmental influences. Trans-theoretical change models describe the recovery process. Trauma-informed approaches recognize developmental impacts. Effective treatment integrates insights from multiple models, recognizing that addiction is too complex for any single framework to fully capture. Different models may be more or less relevant for different individuals at different points in their journey. The person whose addiction arose primarily from untreated trauma needs different interventions than someone whose addiction arose primarily from genetic vulnerability and peer influence, even though both benefit from understanding the neurobiological mechanisms involved. This plurality of models reflects the maturity of addiction psychology as a field. Rather than seeking a single, true explanation, contemporary approaches recognize that addiction is a multiply determined phenomenon requiring multiple perspectives for comprehensive understanding. This theoretical diversity, far from being a weakness, represents the field's ability to capture addiction's genuine complexity. Pathways to treatment. Evidence-based approaches. Understanding the mechanisms of addiction would be of little value if it didn't point toward effective interventions. Fortunately, decades of research have identified numerous evidence-based treatments that significantly improve outcomes for people with substance use and behavioral addictions. These treatments work through different mechanisms, targeting various aspects of the addictive process, and they're most effective when tailored to individual needs and circumstances. Cognitive behavioral therapy, or CBT, stands as one of the most extensively researched and widely implemented psychotherapeutic approaches for addiction. The fundamental premise of CBT is that addictive behaviors are learned patterns maintained by thought processes and environmental triggers, and that these patterns can be unlearned or modified through systematic intervention. CBT for addiction typically includes several key components. Functional analysis involves carefully examining the circumstances surrounding substance use, what triggers use, what immediate and delayed consequences follow, what thoughts and feelings arise before, during, and after use. This detailed mapping helps identify specific high-risk situations, internal states, and cognitive processes that maintain the addictive behavior. Once these patterns are identified, CBT helps develop alternative coping skills. If someone consistently uses alcohol to manage social anxiety, they need new skills for managing that anxiety. Perhaps relaxation techniques, cognitive restructuring, or gradual exposure to feared social situations. If someone uses drugs to cope with boredom or emptiness, they need help identifying meaningful activities and building a life that doesn't require chemical escape. Cognitive restructuring targets the thought patterns that support continued use. These might include permission-giving beliefs. I deserve to relax with a drink after this stressful day. Minimizing consequences. It's not really that bad. Positive expectancies. I'll be more confident if I'm high. Or negative self-talk that creates emotional distress that then triggers use. CBT teaches people to identify these automatic thoughts, examine their validity, and develop more balanced, realistic cognitions. Relapse prevention, a specific form of CBT developed by Alan Marlett, focuses on the high-risk period after initial cessation. This approach identifies situations, emotional states, and thought patterns that increase relapse risk and develops specific strategies for managing these risks. It also addresses the abstinence violation effect, the tendency to interpret a single lapse as complete failure, which can trigger full relapse. By normalizing lapses as part of the recovery process rather than catastrophizing them, relapse prevention helps people return to abstinence more quickly after setbacks. Research on CBT for addiction consistently demonstrates its effectiveness. Meta-analysis combining results from hundreds of studies show that CBT significantly reduces substance use and improves psychosocial functioning compared to no treatment or minimal intervention. Effects persist long after treatment ends, suggesting CBT helps people develop durable skills rather than just managing acute symptoms. CBT works for virtually all substance use disorders and many behavioral addictions, making it a versatile first-line treatment. Motivational interviewing, developed by William Miller and Stephen Rolnick in the 1980s, represents a different therapeutic approach focused specifically on enhancing motivation to change. Many people with addiction feel ambivalent. Part of them wants to quit, while part wants to continue using. Traditional confrontational approaches, which challenge denial and push people toward change, often backfire by triggering defensiveness and resistance. Motivational interviewing instead works with ambivalence rather than against it. The therapist maintains a curious, non-judgmental stance, helping the person explore their own reasons for change while acknowledging the benefits they perceive in continued use. The approach relies on several core principles: expressing empathy, developing discrepancy between current behavior and valued goals, rolling with resistance rather than confronting it, and supporting self-efficacy by affirming the person's capacity for change. A typical motivational interviewing session might involve asking open-ended questions about the person's substance use, its effects on their life, and their goals and values. The therapist reflects back what they hear, particularly any change talk, statements expressing desire, ability, reasons, or need for change. By selectively reinforcing change talk, the therapist helps the person strengthen their own motivation without directly arguing for change. Research shows that motivational interviewing, particularly when delivered as a brief intervention early in the course of problematic use, can significantly increase readiness to change and engagement in treatment. It works particularly well as a prelude to other interventions like CBT, first building motivation, then teaching skills. Studies of motivational interviewing for alcohol use disorders, cannabis use, and tobacco dependence consistently show positive effects, though effect sizes are typically modest. Medication-assisted treatment, or MAT, has revolutionized treatment for opioid use disorder and shows promise for other addictions as well. For decades, addiction treatment was primarily behavioral. Medications were seen as replacing one addiction with another. This view has gradually given way to recognition that medications targeting the neurobiological mechanisms of addiction are not only acceptable, but often necessary for effective treatment. For opioid use disorder, 3 FDA-approved medications form the foundation of ICI-AT. Methadone, a long-acting opioid agonist, occupies mu-opioid receptors, preventing withdrawal and craving without producing significant euphoria. Buprenorphine, a partial opioid agonist, provides similar benefits with lower overdose risk and easier regulatory requirements. Naltrexone, an opioid antagonist, blocks opioid receptors, preventing any effects from opioids if someone does use. The evidence supporting MAT for opioid use disorder is overwhelming. Studies consistently show that people receiving MAT have significantly higher rates of treatment retention, lower rates of ongoing opioid use, reduced overdose mortality, and better overall functioning compared to behavioral treatment alone. MAT doesn't just help people stop using heroin or prescription opioids, it literally saves lives by dramatically reducing overdose risk. For alcohol use disorder, several medications show efficacy. Naltrexone blocks the rewarding effects of alcohol, reducing the likelihood that drinking will escalate. Acamprosate helps normalize neurotransmitter function disrupted by chronic alcohol use, reducing cravings and withdrawal symptoms. Disulfiram creates an immediate, unpleasant reaction if someone drinks alcohol, serving as a deterrent. While these medications aren't effective for everyone, they significantly improve outcomes when combined with behavioral treatment. Nicotine replacement therapy, including patches, gum, and lozenges, along with medications like bupropion and varenicline, substantially increases smoking cessation rates. The medications address the neurochemical dependence, while behavioral interventions address psychological and behavioral aspects of smoking. Despite strong evidence for medication-assisted treatment, access remains limited and stigma persists. Many addiction treatment programs don't offer MAT, often based on philosophies viewing any medication use as simply replacing one drug with another. This perspective is not supported by evidence. MAT is the most effective approach for opioid use disorder, and refusing to offer it effectively denies people the best available treatment. Expanding MAT access and addressing philosophical objections to its use represents an urgent public health priority. Contingency management applies operant conditioning principles to addiction treatment. The approach provides tangible rewards, typically vouchers or cash, for objective evidence of abstinence, usually verified through drug testing. This might seem simplistic, but research demonstrates it's remarkably effective, particularly for stimulant use disorders where no effective medications exist. The rationale is straightforward. Addiction involves a disorder of reward processing, where the addictive substance or behavior has become disproportionately valuable compared to other rewards. Contingency management attempts to rebalance this by making abstinence tangibly rewarding. Critics argue this is simply paying people not to use drugs, which seems to miss the point. If it works, if it helps people establish and maintain abstinence while they develop other sources of meaning and motivation, then it's a valuable intervention. Studies of contingency management show substantial effects, particularly for cocaine and methamphetamine use disorders. When combined with other treatments like cognitive behavioral therapy, it produces better outcomes than either approach alone. The challenge has been implementation. Providing tangible rewards requires funding, and many treatment programs and insurance companies resist paying for what feels like bribing people to do something they should want to do anyway. This resistance ignores evidence in favor of philosophical objections, ultimately harming people who could benefit. 12-step facilitation, an approach designed to help now. People engage with mutual help groups like Alcoholics Anonymous or Narcotics Anonymous, represents an intervention that's simultaneously one of the most widely used and most debated. 12-step groups follow a specific model. Addiction is a disease characterized by powerlessness over the substance. Recovery requires admitting powerlessness and seeking help from a higher power. Maintaining sobriety requires ongoing group participation and working through sequential steps. Research on 12-step facilitation shows it can be effective, particularly for alcohol use disorder. Studies find that people who actively participate in AA, particularly those who get a sponsor and work the steps, have better long-term outcomes. The question is whether this reflects the program's effectiveness or selection bias. Perhaps people who engage deeply with AA are those who are already more motivated or had stronger recovery trajectories. Controlled studies designed to separate effectiveness from selection generally support AA's efficacy, though results are mixed. The social support, Accountability and sense of community provided by 12-step groups appear valuable, independent of specific program elements. However, the emphasis on powerlessness and higher power doesn't resonate with everyone, and alternative mutual help groups, Smart Recovery, Refuge Recovery, Women for Sobriety, provide options for people who struggle with 12-step philosophy. Therapeutic communities represent intensive, long-term residential treatment, typically 6 to 18 months, based on the idea that addiction reflects disorder in the whole person, and that recovery requires comprehensive personal transformation facilitated by an intentional community. Residents take increasing responsibility for community functioning, receive intensive group therapy, and gradually reintegrate into outside society. Evidence for therapeutic communities is mixed but generally positive, particularly for people with severe addiction and extensive social disruption. The challenge is that completing long-term residential treatment requires enormous commitment and typically means extensive time away from work, family, and other responsibilities. Therapeutic communities work best for people who lack stable housing, are deeply embedded in drug culture, or haven't succeeded with less intensive approaches. Family therapy approaches recognize that addiction occurs within social contexts, and that family systems can both contribute to and help resolve substance use problems. Family therapy might focus on improving communication, establishing appropriate boundaries, reducing enabling behaviors, addressing family trauma, or improving overall family functioning. Evidence supports family therapy, particularly for adolescents and young adults, where family involvement is critical. Digital therapeutics, a newer category of intervention, uses technology to deliver evidence-based treatment. This might include apps, providing CBT skills training, digital contingency management platforms, online mutual help groups, or virtual reality exposure therapy for cue-triggered cravings. The pandemic accelerated adoption of telehealth for addiction treatment, and evidence suggests that remote delivery can be as effective as in-person treatment while dramatically improving accessibility. Harm reduction approaches, while sometimes controversial, represent an important part of the treatment landscape. These approaches accept that some people aren't ready or willing to quit substance use entirely, but want to reduce associated harms. Harm reduction might include supervised injection sites, needle exchange programs, medication-assisted treatment without abstinence requirements, or strategies for safer use. Critics argue that harm reduction enables continued use rather than promoting recovery, but evidence doesn't support this concern. People engaging with harm reduction services are more likely to enter treatment, reduce use, and survive to eventually achieve recovery than those who don't. The fundamental principle is pragmatic. Perfect abstinence isn't realistic for everyone at every time, and reducing harm while keeping people alive creates opportunities for eventual recovery. Effective addiction treatment rarely involves a single intervention. The most successful approaches combine multiple evidence-based practices tailored to individual needs. Someone might receive motivational interviewing to build readiness for change, medication-assisted treatment to reduce withdrawal and cravings, cognitive behavioral therapy to develop coping skills, contingency management to reinforce abstinence, and connection to mutual help groups for ongoing support. This comprehensive approach, often called treatment that addresses all dimensions of the person, biological, psychological, social, reflects current best practices. Treatment should assess and address co-occurring mental health conditions, involve family when appropriate, connect people to social services, help with employment or education, and create a foundation for long-term recovery. The goal isn't just stopping substance use, but building a life where substance use is no longer necessary or appealing. One crucial insight from treatment research is that addiction is a chronic, relapsing condition requiring ongoing management, not a problem that can be permanently fixed with a single episode of treatment. Relapse rates for addiction are comparable to rates for other chronic conditions like diabetes or hypertension. This doesn't mean treatment fails. It means recovery is a process, often involving multiple treatment episodes that extends over years. This understanding argues for continuing care models, where intensive initial treatment transitions into lower intensity but ongoing support. This might include periodic check-ins, ongoing medication management, continued participation in mutual help groups, or access to services during high-risk periods. Just as someone with diabetes needs ongoing medical management even when their blood sugar is controlled, someone with addiction benefits from ongoing support even when they're maintaining abstinence. The variety of evidence-based treatments available is both encouraging and challenging. It's encouraging because different approaches work better for different people. When one approach doesn't fit, alternatives exist. It's challenging because determining which approach is best for which person at which time requires clinical expertise and individualized assessment. No single treatment works for everyone, but virtually everyone can find something that works with appropriate matching and adequate support. Recovery and neuroplasticity. The brain's capacity to heal. If understanding the neurobiology of addiction reveals how profoundly the brain changes during active addiction, then understanding neuroplasticity, the brain's capacity to reorganize itself, reveals why recovery is possible even after years of problematic use. The same neural adaptability that allows addiction to develop also enables healing, though this healing requires time, often extensive time, and occurs gradually rather than all at once. The term neuroplasticity refers to the brain's ability to modify its own structure and function in response to experience. This occurs at multiple levels. New connections between neurons can form, existing connections can strengthen or weaken, neurons can change their properties, and in some regions, new neurons can even be generated. Far from being fixed after childhood, as scientists once believed, the brain retains remarkable capacity for change throughout life. During active addiction, neuroplasticity works against the person. The intense, repeated activation of reward circuits by drugs or compulsive behaviors creates robust neural associations. Brain regions involved in executive control, the prefrontal cortex particularly, show reduced gray matter volume, decreased metabolic activity, and impaired connectivity with other regions. The balance of power between reward-seeking circuits and executive control circuits shifts decisively toward reward-seeking. In early recovery, the situation can actually feel worse before it gets better. Someone who's just detoxed might be thinking more clearly than during active use, but their brain is still operating with depleted dopamine systems, upregulated stress circuits, and diminished prefrontal control. Natural rewards, food, social interaction, accomplishments, don't feel particularly rewarding because the dopamine system is still adapted to artificial stimulation. This is the neurobiological underpinning of anhedonia during early recovery, and it's a significant risk factor for relapse. But with sustained abstinence, something remarkable begins to happen. Something that offers genuine hope. Dopamine receptors that were downregulated during active use gradually return to normal density. This process isn't rapid, and this is crucial to understand. Studies using PET imaging to track dopamine receptor density over time suggest it can take a year or more for substantial recovery, sometimes longer, depending on the substance and duration of use. But it does happen. The brain heals. As receptor density normalizes, something many people in early recovery thought was impossible starts to occur. Natural rewards begin to feel rewarding again. Food starts tasting good. Music moves you. Laughter feels genuine. The pervasive anhedonia, that flat, empty, nothing matters feeling, gradually lifts. And here's the revelation that changes everything about how we understand recovery. The prefrontal cortex, that executive control center that got weakened during addiction, shows extraordinary capacity for recovery. Studies following people in recovery have documented progressive increases in gray matter volume in prefrontal regions over months to years of abstinence. These aren't just statistical findings. They correspond with real, functional improvements that people can feel. Better impulse control, improved decision-making, enhanced ability to delay gratification, clearer thinking. The executive functions that were compromised during addiction gradually strengthen. The person returns. But, and this is critical, these changes appear to require more than passive abstinence. Actively engaging in recovery supportive activities, therapy, skill building, meaningful work, social connection, exercise, appears to accelerate and enhance these neuroplastic changes. The brain changes in response to experience, so providing new, healthier experiences promotes adaptive changes far more effectively than simply removing the drug and waiting. Research on cognitive rehabilitation for addiction has found that specific training in executive functions can produce both behavioral improvements and corresponding brain changes. Programs targeting working memory, cognitive flexibility, and impulse control show promise in enhancing the prefrontal control that's often impaired in addiction. While these interventions are still being refined, they represent an exciting direction for augmenting traditional treatments. The hippocampus, crucial for memory formation, also shows potential for recovery. Some substances, particularly alcohol, are neurotoxic to hippocampal neurons. Chronic heavy alcohol use is associated with hippocampal shrinkage and memory impairments. But with sustained abstinence, new neurons can be generated in the hippocampus, a process called neurogenesis, and hippocampal volume can partially or fully recover. This corresponds with improvements in memory function that many people report as one of the benefits of recovery. However, some addiction-related changes may be more persistent. The learned associations between environmental cues and drug effects, encoded through long-term potentiation in multiple brain regions, can remain remarkably strong even after years of abstinence. This is why someone can be successfully maintaining recovery for years, then encounter a cue they hadn't encountered during recovery, and experience powerful, unexpected cravings. This doesn't mean these associations are permanent and unchangeable, but it does mean that weakening them requires repeated exposure to cues without the drug reward, a process called extinction learning. This is essentially what happens when someone successfully navigates high-risk situations without using. Each time they encounter a cue and don't use, the cue-drug association weakens slightly. Over time, with many such experiences, the power of cues diminishes. Understanding the time course of neuroplastic recovery has important implications for treatment expectations and relapse prevention. If someone expects to feel dramatically better immediately after detox, they'll likely be disappointed and may conclude that recovery isn't worth it. But if they understand that feeling substantially better may take months, and that gradual improvements will continue for years, they can maintain realistic expectations and persist through the difficult early period. Research on stress systems reveals another dimension of recovery-related brain changes. Chronic substance use dysregulates the hypothalamic pituitary adrenal axis, the body's primary stress response system, leaving people hypersensitive to stress and prone to negative emotional states. This dysregulation contributes to relapse. Stress is one of the most potent triggers for return to use. With sustained recovery, stress system function gradually normalizes. Baseline cortisol levels, which may be elevated during active addiction and early recovery, return to healthier ranges. Stress reactivity, how intensely the stress system responds to challenges, becomes more appropriately calibrated. This doesn't happen automatically with abstinence alone, but is accelerated by stress management practices, meditation, exercise, therapy, social support. Sleep provides another window into recovery-related brain changes. Addiction severely disrupts sleep architecture, and sleep disturbances can persist for months into early recovery, contributing to mood problems, cognitive impairment, and increased relapse risk. But over time, with good sleep hygiene and sometimes medical support, sleep patterns normalize. Better sleep then supports brain healing in multiple ways, as sleep is crucial for memory consolidation, emotional regulation, and cellular repair processes. The role of exercise in promoting brain health during recovery deserves particular attention. Aerobic exercise increases production of brain-derived neurotrophic factor, or BDNF, a protein that supports neuronal health, promotes neurogenesis, and enhances neuroplasticity. Studies have found that regular exercise during recovery is associated with improved treatment outcomes, reduced cravings, better mood, and enhanced cognitive function. Exercise might be thought of as a neuroplastic intervention. It directly promotes the brain changes that support recovery. Meditation and mindfulness practices also show promise as neuroplastic interventions. Brain imaging studies have documented structural and functional changes in regions involved in attention, emotion regulation, and self-awareness among experienced meditators. For people in recovery, mindfulness practice can help weaken the automatic link between cues and cravings, enhance awareness of thoughts and feelings without being controlled by them, and develop the capacity to observe urges without acting on them. The social dimension of recovery also has neurobiological correlates. Human brains are fundamentally social organs, shaped by and responsive to social interactions. Chronic isolation or chaotic social relationships during active addiction can affect brain regions involved in social cognition and emotional regulation. Building healthy relationships, connecting with supportive communities, and experiencing consistent positive social interactions promotes healing in these social brain networks. This helps explain why mutual help groups, supportive relationships, and therapeutic alliances are so important in recovery. They're not just providing practical support or useful advice, they're actually helping rewire social brain systems that may have been damaged or distorted during addiction. Every positive social interaction is a neuroplastic opportunity, gradually strengthening the neural circuits that support healthy relationships. One of the most encouraging findings from long-term recovery research is that outcomes continue to improve the longer someone maintains recovery. This isn't just about avoiding substance-related problems accumulating. It's about positive changes accumulating. People who maintain recovery for 5 years are more likely to still be in recovery 10 years later. Brain function continues improving. Physical health improves. Relationships heal, and life circumstances stabilize. The brain in long-term recovery can look remarkably similar to a brain that never experienced addiction. Yet it would be misleading to claim that the addicted brain fully returns to its pre-addiction state. Some changes may persist indefinitely. The capacity for drug-related cues to trigger cravings, though diminished with time, may never completely disappear. The vulnerability that contributed to developing addiction in the first place, whether genetic, psychological, or environmental, doesn't go away with recovery. This is why recovery is best understood not as returning to a previous state, but as achieving a new, healthier state that incorporates the reality of having experienced addiction. Someone in long-term recovery develops awareness of their triggers, builds skills for managing cravings, creates a life structure that supports continued recovery, and remains vigilant about maintaining the practices that keep them well. This isn't a defect or limitation, it's an adaptation, a form of wisdom earned through experience. The neuroplasticity literature fundamentally challenges nihilistic views of addiction as permanent brain damage that dooms people to lifelong struggle. While addiction does involve real, significant changes to brain structure and function, these changes are not necessarily permanent. The brain that learned addiction can learn recovery. The neural circuits that were hijacked can be restored. The executive functions that were compromised can be rehabilitated. This capacity for healing isn't just theoretical, it's documented in hundreds of studies examining brain structure and function during recovery, and it's reflected in the millions of people who have successfully recovered from addiction and built meaningful, fulfilling lives. Recovery is not only possible, but achievable with appropriate support, and the brain's remarkable neuroplasticity is a biological foundation for hope. The social and cultural dimensions, the environmental context. While much of our discussion has focused on individual neurobiology and psychology, addiction doesn't occur in a vacuum. It arises within social and cultural contexts that profoundly influence who develops addiction, what form it takes, and whether recovery is accessible. Understanding these broader environmental factors is essential for a comprehensive picture of addiction. Poverty and socioeconomic disadvantage represent perhaps the most powerful social determinants of addiction risk. The relationship is complex and bidirectional. Poverty increases risk for addiction, and addiction can lead to poverty. But the causal arrow pointing from poverty to addiction is well established. Financial stress, housing insecurity, food insecurity, and lack of opportunity create chronic activation of stress systems, which in turn increases vulnerability to addiction as a coping mechanism. Communities experiencing concentrated poverty also typically have higher substance availability and lower access to treatment resources. Liquor stores may be abundant, while quality addiction treatment facilities are scarce. This creates an environment where risk factors are high and protective factors are low, a perfect storm for addiction to flourish. The role of trauma, particularly early childhood trauma, deserves emphasis within this social context. The Adverse Childhood Experiences study, which we've mentioned previously, revealed that experiences like abuse, neglect, household dysfunction, and witnessing violence are common and have dose-dependent effects on later substance use. These aren't simply psychological scars. They're events that literally shape developing brains, altering stress response systems, and emotional regulation capacities in ways that increase addiction vulnerability. Importantly, adverse childhood experiences are not evenly distributed across populations. They're more common in communities experiencing poverty, racism, and social marginalization. The intergenerational transmission of trauma creates cycles where parents who experienced adversity, who may themselves struggle with addiction or mental health problems, raise children in environments where adverse experiences are more likely. Breaking these cycles requires intervention at community and societal levels, not just individual treatment. Racism and discrimination constitute trauma exposure that affects addiction risk. The chronic stress of experiencing racism, the vigilance required to navigate discriminatory environments, and the psychological impact of systemic marginalization all contribute to dysregulated stress systems. Research has found higher rates of substance use disorders among racial and ethnic minorities, particularly once you account for disparities in access to treatment and the criminalization of substance use that disproportionately affects minority communities. The stigma attached to addiction itself functions as a powerful social determinant. People experiencing addiction face discrimination in employment, housing, healthcare, and interpersonal relationships. This stigma creates barriers to seeking help. People fear judgment, loss of respect, or practical consequences like losing their job or custody of children if their addiction becomes known. The shame associated with addiction is itself traumatic and can maintain substance use as a way to manage that shame. Even within healthcare systems, stigma affects care quality. Studies have found that healthcare providers often hold more negative attitudes toward people with substance use disorders than toward people with other medical conditions. This can result in substandard care, dismissive treatment, or reluctance to prescribe necessary medications like medication-assisted treatment. Addressing stigma within healthcare requires recognizing it as a medical condition deserving competent, compassionate treatment. The criminalization of substance use and the war on drugs have profoundly shaped the landscape of addiction in the United States and globally. Rather than treating addiction as a public health issue, drug use has been primarily addressed through criminal justice mechanisms. The result has been mass incarceration, particularly of Black and brown people, with devastating effects on individuals, families, and communities. Research consistently shows that incarceration does not effectively address addiction and typically makes outcomes worse. Prisons rarely provide adequate treatment. The trauma of incarceration, the disruption to social support and employment, and the barriers to reintegration created by a criminal record all increase relapse risk. Yet in many jurisdictions, criminal justice remains the primary system responding to addiction, consuming resources that could fund treatment while failing to improve public health or safety. Alternative approaches, implemented in places like Portugal, demonstrate that decriminalization of drug possession, combined with expanded treatment access, can reduce drug-related deaths, disease transmission, and social costs while actually reducing drug use. These results challenge assumptions that legal deterrence is necessary to discourage use and suggest that treating addiction as a health issue produces better outcomes for individuals and society. Access to treatment represents another crucial social determinant. Addiction treatment is effective when people can access it, but access is far from universal. Insurance coverage for addiction treatment has historically been worse than for other medical conditions, though the Mental Health Parity and Addiction Equity Act and the Affordable Care Act have improved this somewhat. Still, many people lack insurance, and even among the insured, finding providers who accept insurance and have capacity to take new patients can be challenging. Geographic disparities exacerbate access problems. Rural areas often have few addiction treatment providers, requiring people to travel long distances for care. Urban areas may have more providers, but often not enough to meet demand, resulting in waiting lists. The distribution of specialized services like medication-assisted treatment is particularly uneven, with some regions having excellent access, while others have almost none. The philosophy and quality of available treatment varies enormously. Some programs offer evidence-based practices delivered by well-trained professionals. Others rely on outdated approaches, untrained staff, or harmful practices like refusing medication-assisted treatment. The lack of quality standards and the absence of accountability mechanisms mean that someone seeking treatment may have difficulty distinguishing effective from ineffective providers. Cultural factors shape both the form addiction takes and responses to it. Different cultures have different relationships with various substances, different norms around use, and different frameworks for understanding problematic use. What's considered normal drinking in one culture may be viewed as excessive in another. The acceptability of cannabis use, the stigma around opioid use, the role of alcohol in social rituals, all vary across cultural contexts. Treatment approaches need to be culturally adapted to be maximally effective. This doesn't mean fundamentally different treatments for different groups. Evidence-based treatments work across cultures. But implementation matters. Language accessibility, cultural competence among providers, incorporation of cultural healing practices, and attention to how addiction intersects with cultural identity and experience all affect treatment engagement and outcomes. Family and community structures also vary culturally in ways that affect recovery support. In cultures with strong extended family networks, engaging family in treatment and recovery can be particularly beneficial. In cultures where individualism is more emphasized, peer support networks might be more crucial. Understanding these contextual factors allows for treatment that works with rather than against cultural strengths. The social epidemiology of addiction, how rates of substance use disorders vary across populations and over time, reveals that addiction is not randomly distributed. It clusters in certain communities, affects certain populations more severely, and responds to social and policy changes. The opioid epidemic, for instance, has disproportionately affected white working-class communities, particularly in regions experiencing economic decline. This pattern points to social determinants: economic dislocation, loss of community cohesion, and overprescription of pain medications all contributed to creating conditions where opioid addiction could flourish. Understanding these social and cultural dimensions doesn't diminish individual agency or remove personal responsibility. But it does contextualize individual choices within broader circumstances that shape what options are available, what information and support people have access to, and what consequences different choices carry. Two people with similar genetic vulnerability and psychological risk factors may have entirely different addiction trajectories. If one grows up in a stable, supportive environment with strong preventive education and accessible treatment, while the other grows up in chaos, trauma, and social marginalization. Effective addiction response requires intervention at multiple levels: individual treatment for those affected, community-level prevention and harm reduction, systemic changes to improve treatment access and quality, and policy changes to address the social determinants that create vulnerability in the first place. No amount of individual treatment can compensate for social conditions that continuously generate new cases of addiction. This is why comprehensive approaches to addiction increasingly emphasize community-level interventions, improving economic opportunities, strengthening families and communities, reducing trauma exposure, addressing discrimination, improving schools, creating youth development programs, ensuring housing stability. These upstream interventions, while not traditionally thought of as addiction treatment, may ultimately be more effective at reducing addiction's prevalence than downstream treatment alone. The social and cultural context of addiction reminds us that while neurobiology provides crucial insights into mechanisms, addiction is ultimately a biopsychosocial phenomenon that can only be fully understood and effectively addressed by attending to all three levels simultaneously. The brain doesn't exist independently of the body, and neither exists independently of the social and cultural environments that shape development, experience, and opportunity. Closing reflections. Understanding toward compassion. We've traveled a long distance together tonight through the psychology, neurobiology, and social contexts of addiction. From the molecular mechanisms of dopamine, signaling to the broad sweep of cultural influences, from the intimate details of brain structure to the systemic forces shaping entire communities, addiction reveals itself as perhaps the most complex condition the human mind can experience. What emerges from this comprehensive view is a picture very different from the simplistic narratives that have dominated public understanding for so long. Addiction is not a moral failing, not a simple lack of willpower, not a choice in any straightforward sense. It's a medical condition arising from the interaction of genetic vulnerability, neurobiological mechanisms, psychological factors, and social circumstances. It involves real, measurable changes in brain structure and function. It's chronic, often relapsing, and requires professional treatment. Yet addiction is also not deterministic or hopeless. The same neuroplasticity that allows addiction to develop also enables recovery. Treatment works. People recover. The brain heals. Lives are rebuilt. The journey may be long and difficult, with setbacks and challenges, but it's a journey countless people have successfully made. Understanding addiction's complexity should increase compassion, not just because compassion is kind, but because it's scientifically accurate. When someone struggles with addiction, they're not demonstrating weak character. They're experiencing a condition that hijacks the very brain systems responsible for making adaptive choices. The behaviors that look self-destructive or irrational from the outside reflect altered reward processing, impaired executive function, and dysregulated stress systems from the inside. This understanding also illuminates why simple solutions, just stop using, just say no, are inadequate. If addiction were simply about knowledge and choice, then learning about the consequences of use would be sufficient to prevent or cure it. But addiction fundamentally alters the neural systems that translate knowledge into action. The person may understand perfectly well that continued use is harmful, may genuinely want to quit, and yet find themselves unable to execute that intention when confronted with cues or cravings that trigger overwhelming urges. For those experiencing addiction, this understanding offers permission to seek help without shame and persistence through difficulties without self-blame. For families and loved ones, it provides a framework for supporting recovery while maintaining appropriate boundaries. For society, it points toward treating addiction as the public health issue it is, focusing resources on prevention, treatment, and recovery support rather than punishment and criminalization. The digital age has introduced new dimensions to addiction that previous generations never confronted. The smartphone represents perhaps the most potent behavior modification device ever created, designed with sophisticated understanding of psychology to capture and hold attention. Social media platforms, games, and infinite content streams provide unpredictable rewards on demand, creating dopamine hits that can rival those from substances. We're all, to some degree, swimming in potentially addictive stimuli. Yet awareness creates opportunity. Understanding how these technologies exploit reward systems allows for developing healthier relationships with them. Setting boundaries, using tools to limit access, creating technology-free times and spaces, choosing face-to-face interaction over digital connection. These practices, informed by understanding of underlying mechanisms, can help prevent digital behaviors from becoming compulsive. The research on addiction continues to evolve, with new discoveries regularly revising our understanding. Advances in brain imaging allow us to watch neural changes as they happen. Genetic studies reveal ever more of the complex architecture of vulnerability. Longitudinal studies following people over decades illuminate long-term trajectories and recovery processes. Each advance deepens our ability to understand, prevent, and treat addiction. But perhaps the most important insight isn't scientific, but human. Addiction, for all its neurobiological complexity, ultimately reflects something profoundly human: the drive to feel better, to escape pain, to find connection and meaning. Substances and behaviors become addictive not because they're inherently evil, but because they offer, at least initially, something valuable. Relief from suffering, connection with others, temporary escape from difficulty, pleasure in a life that may otherwise feel devoid of it. Recovery, then, isn't primarily about giving up something bad. It's about discovering or rediscovering sources of meaning, connection, and pleasure that don't come with the destructive costs of addiction. It's about building a life that's genuinely worth being sober for. This process looks different for every person, but the fundamental elements are similar: healing relationships, finding purpose, developing coping skills, building community, creating daily structure that supports well-being. The millions of people in recovery around the world demonstrate that this is possible. They show that brains can heal, that lives can be rebuilt, that hope is justified even after years of seemingly hopeless struggle. And here's a final revelation that should fundamentally change how we think about addiction. Research tracking people over decades reveals a pattern that offers genuine hope. Studies suggest that after 5 years of sustained recovery, relapse rates drop dramatically, with some research indicating they fall to approximately 15% or lower, which is comparable to or better than relapse rates for many chronic medical conditions like hypertension or diabetes. After 10 years, brain imaging studies have shown that brain function in recovered individuals can be remarkably similar to those who never experienced addiction, though some subtle differences may persist. While the evidence strongly suggests recovery is achievable, individual experiences vary based on factors like severity of addiction, type of substance, treatment quality, and social support. The damage isn't permanent. The sentence isn't life. This success doesn't erase the difficulty of the journey or minimize the seriousness of addiction. But it proves that recovery is not only possible, it's the likely outcome for people who maintain treatment and support long enough for their brains to heal. The first year is the hardest. The second year is easier. Each year after gets progressively better. The disease that once seemed insurmountable becomes, with time and support, a chapter in the story rather than the entire narrative. But here's the final twist, the one that should make you rethink everything you just heard, based on what emerging neuroscience research is revealing. Remember that phone in your pocket we started with, the one that's more addictive than cocaine, the one you're checking 58 times a day? Here's what a growing body of neuroscience research is increasingly suggesting. That compulsion you feel, that difficulty putting it down, that anxiety when it's not nearby, the evidence indicates that's not categorically different from addiction. It appears to exist on a spectrum. It's the same fundamental mechanism, just at a different intensity. Which means this entire exploration hasn't just been about understanding people with diagnosable addiction. Based on what we now know about reward systems and compulsive behavior, it's been about understanding all of us. Every person watching this has experienced the wanting system overriding the rational system. Every person has felt cravings they couldn't quite explain. Every person has engaged in behavior they knew wasn't serving them, but felt compelled to continue anyway. What the research suggests is profound. Addiction isn't some separate category of human experience that happens to other people who are different from you. It appears to be an extreme manifestation of how all human brains work, of how reward systems that served us beautifully for millions of years can be exploited by stimuli they never evolved to encounter. The person deep in substance addiction and the person who can't stop scrolling social media aren't experiencing different phenomena. They're experiencing the same phenomenon at different points on a continuum. The mechanisms are identical. The intensity differs. And this changes everything about how we should think about vulnerability. Because if we're all on this spectrum, if we all have reward systems that can be hijacked, then the question isn't, why do some people become addicts? The question is, what protects most of us from progressing further along this spectrum, and how do we strengthen those protections for everyone? The answer, emerging from decades of research, suggests it's the same factors we've discussed tonight. Strong social connections, meaning and purpose, coping skills for stress, awareness of our vulnerabilities, environments that support well-being rather than exploitation, and access to help when we need it. Understanding addiction, in the end, isn't just about understanding a disease. It's about understanding the human condition in the 21st century, about recognizing that we're all navigating an environment specifically designed to activate our reward systems in ways that can become compulsive. Some of us encounter more extreme versions through substances, but all of us are facing the same fundamental challenge: maintaining agency over our own behavior in a world engineered to override it. That knowledge, that we're all in this together, all vulnerable, all capable of both compulsion and recovery, that might be the most important insight of all. For anyone struggling with addiction, know that help is available and recovery is possible. The shame and isolation that often accompany addiction don't need to be permanent. The brain's capacity for healing, the availability of effective treatments, and the support of communities focused on recovery create real pathways toward a different life. For loved ones of people with addiction, know that while you can't force someone to recover, you can support them in ways that make recovery more accessible. Understanding addiction as a medical condition rather than a moral failing allows for maintaining both compassion and boundaries, offering help without enabling, and preserving relationships through the difficult periods while maintaining appropriate limits. For society, the task is clear. Treat addiction as the public health issue it is, invest in prevention and treatment, address the social determinants that create vulnerability, reduce stigma and barriers to care, and create communities where recovery is supported and celebrated rather than marginalized and hidden. As we close this exploration, take a moment to reflect on what we've discovered. The brain, that remarkable 3-pound universe of neurons and synapses, of chemicals and electricity, is capable of both profound vulnerability and extraordinary resilience. It can learn patterns that become self-destructive, but it can also heal, adapt, and find new ways forward. Addiction is part of the human condition, arising from systems designed to help us survive and thrive, but sometimes leading us astray when confronted with stimuli our evolution never anticipated. Understanding this doesn't make addiction less serious or less requiring of treatment, but it does place it in context, not as alien or mysterious, but as an understandable phenomenon arising from comprehensible mechanisms. And perhaps that's the most powerful insight of all, that by understanding addiction, its causes, its mechanisms, its treatments, we gain power to respond to it more effectively, with more compassion, and with greater hope for those affected. If you found this exploration valuable, consider supporting this channel by liking this video and subscribing for more deep dives into psychological phenomena. Your engagement helps this content reach others who might benefit from understanding. Until next time, may you carry this knowledge gently, use it wisely, and remember that within the complexity of addiction lies also the possibility of recovery, healing, and hope. Good night.